Okay, it looks like I'm live. I am just going to do a little bit of posting just to let people know that I'm live. If you're watching the recording, you might want to skip ahead a few minutes. Okay, all right. So where did we leave off yesterday? Well, we almost finished. Let me just see what it was. Yeah, lecture 8, the quantum harmonic oscillator, part 1 with the guest lecturer Barton Zubak. And basically, to kind of recap what my strategy has been so far is I went through the problem sets. I was thinking about maybe going through all the problem sets, or at least a majority of them. But then when I started going through them, I recognized that, you know what, I'm kind of skimming over a little bit because some of the math is just going over my head. So I don't really understand the questions. So there's sort of a trade-off point. I mean, you can review the problem sets ahead of time, and that's good for kind of queuing up, okay, I need to pay attention to this and this. But at a certain point, it gets too complicated. You're just missing too many concepts to even understand what the questions are asking. And that was sort of where I was hitting around problem set 4. So I decided, you know what, I'm going to switch back to the lectures. It looked like after lecture 10, I should be able to complete problem sets 1 to 5. So I went through all the lectures. Why do it this way as opposed to just doing the problem sets as they come up in the class? Well, there's really a trade-off between two different things. So when I did the MIT challenge, I went the completely other direction. I just did all of the classes, all the lecture videos for the entire course before I touched a single problem in many classes. And I don't think that that's ideal for most students in a learning perspective. I mean, if you are trying to learn a difficult class, it's going to be hard for you to do it that way. On the other hand, if you are doing a project where you are, you feel confident, you can watch all the lectures and still understand what's going on. They don't feel confusing by halfway through because you haven't done the problems. Then one of the advantages of doing them in this big chunk is that, okay, now you've got all the course material in front of you and you can kind of decide where you have to focus your limited time. So during the MIT challenge, I had really restricted time. So very often there just wasn't enough time to do every single problem set available, every single question that I could practice on. And I had to pick and choose, what are my conceptual weak points? What are my calculating weak points? And it was just sort of a process of elimination. So there wasn't always time to do everything perfectly. This time, I do have enough time, I believe, to learn the class completely. Unless there's, a lot of math stuff from previous classes, 1 month should be more than enough time to learn this class well. And so because of that, I'm not going as extreme as I did during the MIT challenge, where I did every class first and then started doing the problem sets. I also think that that's going to be harder to do here for the same reason it was hard to read to the end of the problem sets without doing the classes, because without familiarizing myself with a lot of the mathematical parts, which is what's going to be hard about this, it's very easy to just be jotting down notes in lecture, let's say 20, where you don't even know how to do the stuff in lecture 10, really. And so you're not getting as much benefit. So I kind of chose a different trade-off point here. I'm deciding to do the lectures in 2 bursts up to lecture 10. And then depending on the next ones, probably do the rest of the lectures in 1 more go next week. So today, I want to get up to the end of lecture 10. Now, in lecture 8, we were covering basically solving the partial differential equation that is the Schrodinger equation of the time evolution of the Schrodinger equation. And this is a differential equation. Differential equations are something that I haven't done for 8 years. So there's a little bit of a rustiness there. Not to mention that they were hard when I was doing them 8 years ago. So it wasn't that I had mastered them and they were a breeze almost a decade ago. I remember them being difficult because, like integration, there's no real, it's a little bit like you kind of have to, there's a bit of puzzle solving. They're not just a simple, okay, follow steps 1 to 10 and you will solve the differential equation. Some differential equations have no solution, no analytic solution known, and for a lot of them, you can kind of see out a form, but it's a lot of guessing. You got to sort of be like, well, maybe this is the form of the solution, and all right, well, maybe what about this? And so it's a lot of like, try this, plug this in, work it out. And we're going through this partial differential equation in the class, and oh wow, it's difficult. And so I took some notes on it. I have a couple pages here of him working through this. I guess you can't see my notes here. Let me switch the view. I have a couple pages of notes here of him doing this, you know, solving the harmonic oscillator, of substituting variables and trying different forms of the expression and putting in a power series, and then, you know, doing more substitutions and then trying to get these. So, okay, there's a lot of stuff that was going over my head in this lecture. He's skipping ahead, you could say, for a lot of parts that, you know, just kind of, all right, well, you know, and if you do the calculation, you get this. And then, oh, but, you know, if you try this, you'll discover this. So we're kind of getting the abbreviated version of what is probably a longer process to work through on paper. Now, I kind of ended yesterday wondering out loud whether or not I should really try to understand this, master this differential equation. In favor of it, I don't like not understanding anything in the class. So if there's anything that comes up and I don't feel like I understood it, that's something that's bad. I should try to be fixing that. On the other hand, I kind of know from behind that this is going to be difficult, and that I know that this way of solving the partial differential equation, just sort of by brute force, is maybe not how we're going to be solving them in general. That the kinds of differential equations we're going to be looking at, if they are, you know, things that are going to come up on an exam or things that I might need to consider and actually do the math for, these differential equations, there's probably going to be some kind of hook or trick, or like, well, if you use this form, it becomes way easier. So I think at this point, I'm not going to go through and do a deeper sort of, you know, understanding venture right now. But we do have more time in this class, so I'm going to put a little asterisk by this because this might be something to revisit later. I definitely don't want to touch this until I've done some problem sets, because I think that this could be, you know, an hour or two of me trying to figure out exactly what's going on at every little step of this. You know, maybe not that long, but it could be a considerable amount of time, and I'd rather get done the problem sets, which I think are more indicative of at least what the professors thought were important for understanding this class. And, you know, there's going to be a lot of things like this where, you know, I sort of get it, but I don't fully get it, or I don't have mastery over it. And so for these kinds of concepts, these are also things that I might bring about a little later, unless they're kind of foundational to understanding other things. Just because I think, you know, if I can get through the problem sets and they're A-okay, and I've finished all the lectures and I'm feeling good, now that's a good time to sort of be like, okay, what are the mathematical underpinnings of things that we're doing that I don't feel like are obvious to me? And this would be a good example of one. So given the fact that we have a month, I'm planning on finishing first 5 problem sets and all the lectures by the halfway point. It may be the case that I'm just going to have enough time to go through and do this. But this is an example of just sort of making these kind of decisions of how to decide what you're going to be doing. So without further ado, I'm going to really try to work hard to get to finish lecture 10 this morning. I mean, it really depends on how fast I can go through them. This one here, there was a lot of math. I was going through it at 1x speed for the most part. 1x speed, I mean, they're about an hour and a half each. If it's that length, I maybe can finish. We'll see. I might push a little past 11 today. Yesterday, I had some plans that were happening in the evening, so I kind of had to cut the lecture short, the 10 minutes left mark. I don't usually like to do that. I like to like conclude whatever I was doing mentally before jumping forward, but we'll just get back to it now. So I'm going to switch to going back to the lecture. For those of you watching, these are probably not going to be the most exciting lectures unless you're just interested in my note-taking technique, which, as I said, I don't really feel like the notes I'm taking, people have been asking me for the notes. I mean, if you want to learn the class, my notes are probably not the thing to use. The notes that you would want to use are the class notes delivered by the professor, because these are mostly meant to be a guide for me I'm writing down things that I understand. I'm writing down my own things. They're more a mechanism to pay attention in the class than anything else, as well as, you know, giving me a rough timestamp of when we discuss things. So if I want to go back, I can go through them. All right, so let's go into the lecture. We have, I think, about maybe 10, 15 minutes left of this one. And then we got 2 more, and then it's problem set time, which I'm hoping I can crack this afternoon and make some headway there. So let's switch over here. All right. And then let's go.
To infinity. Now, these two ends.
I'm going to jump back just a little bit, just because I'm.
Whatever the energy is sufficiently large, the most important here is the 2j here, the j and the j, so you get 2 over j aj. So, roughly, for large j, it behaves like that. And now you have to ask yourself the question, if you have a power series expansion whose coefficients behave like that, how badly is it at infinity? How bad is it? You know, it's a power series expansion because your h was all these coefficients, and suppose they behave like that, they grow in that way, or decay in this way because they're decaying. Is this a solution that's going to blow up, or is it not going to blow up? And here comes an important thing. This is pretty bad behavior, actually. It's pretty awful behavior. So let's see that. That's pretty bad. So, how do we see that? Well, you could do it in different ways, depending whether you want to derive that this is a bad behavior or guess it. I'm going to guess something. So I'm going to look at how does e to the u squared behaves as a power series. Well, you know, as a power series, exponential is 1 over n u squared to the n. Here's n factorial. N equals 0 to infinity. Now, these two n's, u to the 2n, these are all even powers. So I'm going to change letters here, and I'm going to work with j from 0 to 4 over the even. So I will write u to the j here. And that is correct, because you'll produce u to the 0, u to the 2, u to the 4th, these things. And j is really 2n, so here you will have 1 over j over 2 factorial. Now you might say, oh, j over 2, isn't it a fraction? No, it's not a fraction because j is even, so this is a nice factorial. Now, this is the coefficient Cj u to the j. And let's see how these coefficients vary. So this Cj is 1 over j over 2 factorial. What is Cj plus 2 over Cj? Which is the analog of this thing? Well, this would be 1 over j plus 2 over 2 factorial. And here is up there, so j over 2 factorial. Well, this has one more factor in the denominator than the numerator. So this is roughly 1 over j over 2 plus 1, the last value of this. This integer is just 1 bigger than that. Now, if j is large, this is roughly 1 over j over 2, which is 2 over j. Oh, exactly that stuff. So, it's pretty bad. If this series goes on forever, it will diverge like e to the u squared, and your h will be like e to the u squared with e to the minus u squared over 2 is going to be like e to the plus u squared over 2. It's going to go and behave like this one. So it's going to do exactly the wrong thing. If this series doesn't terminate, we have not succeeded. But happily, the series may terminate because the j's are integers. So maybe for some energies that are integers, it terminates, and that's the solution. The only way to get a solution is if the series terminates. The only way it can terminate is that the e is some odd number over here. And that will solve the thing. So we actually need to do this. This shows the energy. You found why it's quantized. So let's do it then. Really done with this in a sense. This is the most important point of the lecture, is that the series must terminate. Otherwise, it will blow up horrendously. If it terminates, it's a polynomial and everything is good. So to terminate, you can choose 2j plus 1 minus e to be 0. This will make aj plus 2 equal to 0. And your solution, your h of u, will begin, aj will be the last one that is non-zero, so it will be aj times u to the j, and it will go down like aj minus 2, u to the j minus 2, it will go down in steps of 2, because this recursion is always by steps of 2. So that's it. That's going to be the solution, where these coefficients are going to be fixed by the recursion relation, and we have this. Now, most people here call j equal n. So let's call it n. And then we have 2n plus 1 minus e equals 0, and h of u would be an u to the n plus all these things. That's the h. The full solution is h times e to the minus u squared over 2, as we will see. But recall what e was. E here is 2n plus 1. But E was the true energy divided by h omega over 2. That was long ago. It's gone, long gone. So what have you found, therefore? That the energy that we'll call En, the energy of the nth solution is going to be h omega over 2, 2n plus 1. So it's actually h omega, and people write n plus 1/2. Very famous result. The nth level of the harmonic oscillator has this energy. And moreover, these objects, people choose this, you see the constants are related by steps of 2. So just like you could start with A0 or A1 and go up, you can go down. People call these functions Hermite functions, and they fix the notation so that this an is 2 to the n. They like it. It's a nice normalization. So actually h of u n is what we call the Hermite function of u sub n, and it goes like 2 to the n u to the n plus order u to the n minus 2 plus n minus 4, and goes on and on and on like that. Okay, a couple things and we're done. Just for reference, the Hermite polynomial, if you're interested in it, is the one that solves this equation, and the Hermite sub n corresponds to E sub n, which is 2n plus 1. So the Hermite solution from that equation is that the Hermite polynomial satisfies this, minus 2u dhn du plus 2n, because En is 2n plus 1, so it's 2n hn equals 0. That's the equation for the Hermite polynomial. An interesting thing to know, actually, if you want to generate efficiently the Hermite polynomials, there's something called the generating function. E to the minus z squared plus 2zu, if you expand it in a power series of z, it actually gives you n equals 0 to infinity. If it's a power series of z, it will be some z to the n's. You can put a factor here n, and here is the hn of u. So you can use your Mathematica program and expand this in powers of z, collect the various powers of u that appear with z to the n, and that's hn. It's the most efficient way of generating hn. And moreover, if you want to play in mathematics, you can show that such definition of hn satisfies this equation. So it produces the solution. So what have we found? Our end result is the following. Let me finish with that here. We had this potential, and the first energy level is called E0 and has energy h omega over 2. The next energy is E1. It has 3/2 h omega. Next one is E2, 5/2 h omega. This polynomial is nth degree polynomial, so it has n zeros, therefore n nodes. So these wave functions will have the right number of nodes. E0, the psi 0 will have no nodes. When you have psi 0, the hn becomes a number for n equals 0, and the whole solution is the exponential of u squared over 2. The whole solution, in fact, is, as we wrote, psi n hn of u e to the minus u squared over 2. In plain English, if you use an x, it will be hn. U was x over that constant a we had, and you have minus x squared over 2a squared. Those are your eigenfunctions. These are the solutions. Discrete spectrum, evenly spaced, the nicest spectrum possible. All the nodes are there. You will solve this in a more clever way next time. See.
Wow. Okay. So this was definitely the hardest lecture we've done so far, and I think that you can see he's just finishing on time. So I think that the time pressure of doing this live in the class is part of the reason this was so difficult. That he's just kind of skipping right over things that are hard. And I do remember from doing differential equations before that like integration, there's kind of an easy way and a harder way. So if you kind of know what you need to put in there, the puzzle just falls out. Whereas if you don't know, there's a lot of trial and error. And I think he's trying to show kind of what would be a reasonable thought process to arrive at what is the right way to solve these problems. As I said, I'm not going to go into detail with this yet. I do recognize that I don't fully understand most of the logic behind the steps, although I do understand the outcome that we got at, that we now have this thing right here, which is, I don't know, it's like a kind of polynomial, Gaussian almost, that is the shape of the wave function at these eigenstates, which I think, you know what, I'm going to have to be, this is my guess. I'm just going to put guess right here. But my guess is that these energy eigenstates for this potential well that they look something like this, kind of like that, where you have it going off kind of like a bell curve on the outsides, and then it has some kind of frequency in the middle. So this is, I think, what this is, because this is a Gaussian here. So this is sort of showing how it tapers off. And then I think this is a polynomial. You know what, I have to go through. It was a polynomial. It wasn't sinusoidal, hey? Yeah, I need to go through it a little bit more, but I think it looks kind of like this. This is the thing that we're looking at. Okay, let's go on to lecture 9. I think lecture 9 will also clear things up a little more, just because this was the sort of complicated, hard way of solving the problem, and I think we're going to learn the easy way, and then we can kind of go back and sort of master this at a later point.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
So it's a beautiful recording. Okay, so to get started, questions from last time. So Martin covered for me last time. I fled. I was out of town. I was at a bad conference. It was pretty surreal. Question, yes. About the exam, yes, absolutely. So the exam is, as you all know, on Thursday, weekends. So on Tuesday we'll have a lecture. The material Tuesday will not be covered on the exam. The exam will be a review of everything through today's lecture, including the problem set, which for some technical reason I don't know why it didn't get posted, but it should be up after lecture today. The exam will be a combination of short questions and computations. It will not focus on an enormous number of computations. It will focus more on conceptual things, but there will be a few calculations on the exam. And I will post some practice problems over the next couple of days. You do have a problem to do Tuesday, and that is part of your preparation for the exam. Here's a basic strategy for exams for this class. Anything that's on a problem set is fair game. Anything that's not covered on a problem set is not going to be fair game. If you haven't seen a problem on it, broadly construed, then you won't, I won't test you on a topic where you haven't done problem solving before. But I will take problems and ideas that you've studied before and spin them slightly differently to make you think through them in real time on the exam, okay? So the purpose, from my point of view, the purpose of these exams is not to give you a grade. I don't care about the grade. The purpose of these exams is to give you feedback on your understanding. See the slip through 20 times and be like, oh yeah, I totally got this. This is fun. But it's not always an accurate read, so that's the point. Did that answer your question? Okay, other questions? Exam? Yeah.
So when we solved the two-stage series method, yes. So there are two solutions technically, the even solution and the odd term solution. Good. So did every condition force the other one to be completely zero with a coefficient in front of it? So like there's like an A0 term which determines all the other ones. Yes. But there's like an A0 term and an A1 term for evens and odds. So did the other one just have to be zero?
This is a really good question. So this is an excellent question. Let me ask the question slightly differently and tell me if this is the same question. When we wrote down our differential equation, so last time we did the harmonic oscillator, and Barton gave you the brute force strategy for the harmonic oscillator. We want to find the energy eigenstates because that's what we do to solve the Schrodinger equation. And we turn that into a differential equation, and we solve this differential equation by doing an asymptotic analysis and then a series expansion, right? Now this is a second order differential equation. Everybody agree with that? It's a second order differential equation. However, in our series expansion, we ended up with one integration constant, not two. How does that work? How can it be that there was only one integration constant, not two? It's a second order differential equation. Right? Is this your question? Okay, and this is an excellent question, because it must be true that there are two solutions. It cannot be that there is just one solution. It's a second order differential equation. There are distance and uniqueness theorems which tell us there are two integration constants. So how can it possibly be that there was only one? Well, so we did something rather subtle in that series expansion. In order to, for that series expansion, there was a critical moment, which I'm going to go through, we can go to my office hours again. But just look through the notes. There's an important moment in the notes when we say, aha, these terms matter. But what we did is we suppressed a singular solution. There's a solution of that differential equation which is not well behaved, which is not smooth, and fetal rich divergence. Okay? And we already did from the asymptotic analysis, we already fixed that the asymptotic behavior was exponentially falling. But there's a second solution which is exponentially growing. So what we did, remember how we did this story? We took our wave function and we said, okay, look, we're going to pull off, we're going to first do asymptotic analysis. And asymptotic analysis tells us that either we have exponentially growing or exponentially shrinking solutions. Let's pick the exponentially shrinking solutions. So sine e is equal to e to the minus x over 2a squared times some, I don't remember what Martin called it, I'll call it u of x. So we've extracted, because we know that asymptotically takes this form, well, it could also take the other form, e to the plus, which would be bad, not normalizable. We've extracted that and then we write down the differential equation for u. And then we solve that differential equation by series analysis. Yeah? However, if I have a second order differential equation for phi, this change of variable doesn't change the fact that it's a second order differential equation for u, right? There's still two solutions for u. One of those solutions will be the solution of the equation that has this asymptotic form, but the other solution will be one that has an e to the plus x squared over a squared, so that it cancels off this leading factor, gives me the exponentially growing solution. Remember that? So, in that series analysis, there's a sort of some moment where you impose that you have the convergent solution. So the answer of why did we get a first order relation is that we very carefully, although it may not have been totally obvious, but when doing this calculation, one carefully chooses the convergent solution that doesn't have this function blowing up so as to overwhelm the envelope. That answer your question? Great. Okay, it's a very good question. This is an important something that comes all over the place when you do symptotic analysis. I speak from my heart. It's an important thing, the research that I'm doing right now. Getting these sorts of subtleties right is it can be very confusing. It's important to think carefully through, so it's a very good question. Other questions before we move on? Okay. So, I'm going to erase this because it's not very visual, but it is great. Okay, so one of the lessons of this brute force analysis was that we constructed the spectrum, i.e. the set of energy eigenvalues allowed for the harmonic oscillator, the quantum harmonic oscillator, and we constructed the wave functions. We constructed the wave functions by solving the differential equation through asymptotic analysis, which gave us the Gaussian envelope, and series expansion, which gave us the Hermite polynomials. And then there's some normalization coefficient. And then we got the energy eigenvalues by asking, when does this series expansion converge? When does it terminate, so that we can write down an answer? And that was what gave us these discrete values. But fine, we can see that would be discrete values. We're cool with that. In fact, Barton went through the discussion of the node theorem and the lack of degeneracy in one-dimensional quantum mechanics. So it's reasonable that we get a bunch of discrete energy eigenvalues, as we talked about now for 2 lectures. However, there's a surprise here, which is that these aren't just discrete. They're evenly spaced. We get a tower starting with the lowest possible energy corresponding to a, E0. Starting with the lowest possible energy, which is greater than 0, and a corresponding ground state wave function. And then we have a whole bunch of other states, phi 1, phi 2, phi 3, phi 4, labeled by their energies, where the energies are evenly spaced. Yeah. They needed to be discrete because these are bound states. But evenly spaced is a surprise. So why are they evenly spaced? Anyone? Based on the last lecture's analysis? Yeah, you don't have a good answer to that from last lecture's analysis. One of the mysteries comes out of the brute force analysis. When you take a differential equation, just beat the crap out of it with a stick by solving it with differential equation strategies like this, you don't necessarily get some more subtle structure. One of the goals of today's lecture is going to be to explain why we get this structure. Why, just from the physics of the problem in physics, should you know that the system is going to have evenly spaced eigenvalues? What's the structure? And secondly, I want to show you a way of repeating this calculation without doing brute force analysis that reveals some of that more fine-grained structure of the problem. And this is going to turn out to be one of the canonical moves in the analysis of quantum mechanical systems. So from quantum mechanics to quantum field theory, this is a basic series of logical moves. What I'm going to do today also has an independent life in mathematics, in algebra, and that will be something you'll study in Emergent 105, but I would encourage you to ask the recitation instructors about it, or me, in all sorts. Okay. So our goal is to understand that even spacing, and also to rederive these results without the sort of brutal, direct assault methods we used last time. So what I'm going to tell you about today is something called the operator method. It usually goes under the name of the operator method. So to get us started, let's go back to look at the energy operator for from a calculator, which is what at the end of the day we want to solve. Square root 2m plus m omega squared plus 2 x squared. Okay. And this is the operator that we want to, whose eigenvalues we want to construct, whose eigenfunctions we want to construct. Before we do anything else, we should do dimensional analysis. First thing you do when you look at a problem is do some dimensional analysis, identify the salient scales, and make things to the degree possible dimensional. Your life will be better. So what are the parameters we have available to us? We have h bar because it's quantum mechanics. We have m because we have particle mass m. We have omega because this potential characteristic frequency omega. What other parameters do we have available to us? Well, we have c. That's available to us. But is it relevant? No. It should claim that if you get an answer that depends on the speed of light, you made some horrible mistake, right? So not there. What about the number of students in AO4? No, there are an infinite number of parameters that don't matter to this problem. What you want to know is when you do dimensional analysis, what parameters matter for the problem? What parameters can possibly appear in the answer? And that's it. There are no other parameters in this problem. Yeah, so that's a full set of parameters available to us. This has dimensions of momentum times length. This has dimensions of mass, and this has dimensions of one upon time. And so what characteristic scales can we build using these 3 parameters? Well, this is a momentum times a length. If we multiply by a mass, that's momentum times mass times x, which is almost momentum again. We need a velocity, not a position, but we have one over time. So if we take h bar times m omega, so that's px times m over t, that has units momentum squared. Okay. And similarly, this is momentum, which is x, which is length mass over time. You can divide by mass, divide by frequency, multiply by time. So h bar upon m omega. And this is going to have units of length squared. Okay. And with a little bit of foresight from factors of 2, I'm going to use these to define 2 length scales. X naught is equal to h bar. Oh, I want to be careful to get my coefficients. Yeah, I always put 2 in the place. So 2h bar upon m omega, square root. And I'm going to define p naught is equal to square root of 2h bar times m omega. Okay? So here's my claim. My claim is at the end of the day, the salient length scales for this problem should be integers or dimensionless numbers times this length scale, and salient momentum scale should be this scale. Okay? Just from dimensional analysis. So if somebody doesn't make sense, what do you think is the typical scale? What is the typical size of the ground state wave function? The typical length scale over which the wave function is not 0. Well, that can't possibly be the size of Manhattan. It's not the size of a proton. There's only one length scale to exist, it should give order x9. Always start with dimensional analysis, always. Okay, so with that, we can rewrite this energy. Oh, sorry, there's one last energy. We can write an energy, a thing with energy, which is equal to h bar omega. And this times frequency gives us an energy. Okay. So we can rewrite this energy operator as h bar omega times p squared over p naught. So this is energy, so I think it must be dimensionless. And it turns out to be p squared over p naught squared plus x operator squared over x naught squared. So that's convenient.
Hold on a sec. Squared over p naught squared plus x squared over x naught squared.
So this has nothing to do with the operator method. This is just being reasonable. Okay. Quick note, thing to note. X naught times p naught is just the omegas cancel, so we get root 2 h bar squared, 2 h bar. Okay, so little tricks like that are useful to keep track of as you go. Okay. So we're interested in this operator. We're interested in this energy operator. And it has a nice form. It's the sum of squares. And when you see the sum of squares, a very convenient thing to do is to factor it. So for example, if I have two classical numbers, c squared plus d squared, the mathematician in me screams out to write c minus id times c plus id. I have factored this, and that's usually a step in the right direction. And is this true? Well, yes, it's true. C squared plus d squared and the cross terms cancel. Okay, that's great. 4 complex numbers, or 4 c numbers. Now, is this true for operators? Can I do this for operators? Here we have the energy operator as the sum of squares. Well, let's try it. I'd like to write that in terms of x and p. So what about writing what about writing the quantity x minus I p over x naught over p naught operator times x over x naught plus I p over p naught. Okay. So we can compute this. This is easy. So the first term gives us the x squared over x naught squared. That last term gives us the i's cancel. We get p squared over p naught squared. But then there are cross terms. We have an xp and a minus px with an overall I. So plus I times xp over x naught times p naught. So x naught times p naught, however, is 2h bar. So that's over 2h bar. Okay. And then we have the other term minus px, same thing. So I can write that as the commutator xp minus px. Ever go with that? Unfortunately, this is not what we wanted. We wanted just p squared plus x squared, and what we got instead was p squared plus x squared closed plus a commutator. Happily, this commutator is simple. What's the commutator of x with p? Yeah, exactly. Commit this to memory. Okay, this is
IH bar.
This is your friend.
Yeah.
Okay. So this is just IH bar. So this is equal to ditto plus IH bar. The I, oops, somewhere I got a minus sign. Where did I get my minus sign wrong? X with IP. Oh no, good, this is good. Okay, so X with P is I, so we get an IH bar. No, I really did screw up the sign. How did I screw up the sign? Oh, no, I didn't. Wait, oh, of course, no, good. Sorry. Trust your calculation, not your memory. Okay, so the calculation gave us this. So what does this give us? We get this IH bar. So plus, but the IH bar times I is going to give me a minus. And the h bar is going to cancel because I've got an h bar from here and an h bar at the denominator minus 1/2. So this quantity is equal to the quantity we wanted minus 1/2. And what is the quantity we wanted? X naught squared plus p naught squared. This guy. So putting that all together, we can write that the energy operator, which was equal to h bar omega times the quantity we wanted, is equal to, well, the quantity we wanted is this quantity plus 1/2 h bar omega times, I'll write this as x over x naught plus I p over p naught x over x naught, over x naught minus plus I p over p naught had plus 1/2. Ever go with that? So it almost worked. We can almost factor. So at this point, it's tempting to say, well, that isn't really much an improvement. You've just made it uglier. But consider Just trust me on this one, that this is not a stupid thing to do. So an operator called A, which is equal to x over x naught, plus I p over p naught, and an operator which I will call A dagger. Is that A dagger ACB for me? Over x naught minus I p over p naught. Hamlet quotes are harder. So this is A dagger, and we can now write the energy operator for the harmonic oscillator is equal to h bar omega times A dagger A plus 1/2. Everyone go with that? Now this should look suggestive. You should say, aha, this looks like h bar omega something plus 1/2. That sure looks familiar from our brute force calculation. But, okay, that familiarity is not an answer to the question. Meanwhile, you should say something like this. Look, this looks kind of like the complex conjugate of this guy. Right? Because there's an I, and you change the sign of the I. But what is a complex conjugate of an operator? What does that mean? An operator is like take a vector, rotate. What is the complex conjugation of that? I don't know. So we have to define that. Okay. So I'm now going to start with this a quick math aside. And morally, this is about what is the complex conjugate of an operator. But before I move on, questions.
Oh, someone asked me, do I listen to it normally via speakers? Yeah, I don't think it matters. Sometimes with headphones.
Okay. So here's a mathematical series of facts and claims. So I claim the following. Given any linear operator we can build, there's a natural way to build without making any additional assumptions or any additional ingredients. We can build another operator, O dagger, in the following way. Consider the inner product of f with g, or the bracket of f with g. So integral dx of f complex conjugate g. Okay. Now consider the function we're taking here is actually the operator we have on g. I'm going to define my option. So this is a perfectly good thing. What this expression says is take your function g, act it over the operator o, multiply by f complex conjugate, take the integral. This is what we would have done if we had taken the inner product of f with the state we get by, or the function we get by taking o and acting on the function g. So now here's the thing. What we want to do is define a new operator, and here's how I'm going to define it. I'm going to define it by choosing how it acts. I'm going to tell you exactly how it acts, and then we'll define the operator. So this operator, O with a dagger, called the adjoint, is defined in the following way. This is whatever operator you need such that the integral gives you, such that the following is true, integral dx O on f complex conjugate g. Okay, so this is the definition of this dagger action, the adjoint action. Okay, so O dagger, this is the adjoint. And sometimes it's called the Hermitian adjoint. I'll occasionally say Hermitian, occasionally not, with no particular order to it. So what does this mean? This means that whatever O dagger is, it's that operator that when acting on G and then taking the inner product with F gives me the same answer as taking my original operator and acting on F and taking the inner product with G. Cool? So we know if we know what our operator O, the challenge now is going to figure out what must this O dagger operator be such that this expression is true. That's going to be my definition of the adjoint. Cool? So I'm going to do a bunch of examples and walk through this. Okay. So the mathematical definition is that an operator O defined in this fashion is the Hermitian adjoint of O.
Hermitian.
Okay, so that's the mathematical definition. Well, that's our version of the mathematical definition. I just came back from math conference, so I'm particularly chastened. Be careful. Okay, so let's do some quick examples. Example 1. Suppose C is a complex number number is also an operator? It acts by multiplication. The number 7 is an operator because it takes a vector and it gives you 7 times that vector. Okay, so this number is a particularly simple kind of operator. And what's C adjoint? Okay, well, we can do that. That's easy. So C adjoint is going to be defined in the following way. It's integral dx f star of C adjoint G is equal to the...
Hold on a sec. F star. Sometimes it's useful to just pause the lecture and go ahead and try to see if you can anticipate what's happening. That's a good check on understanding. So this has got to be symmetrical to this. So that's going to be dx of C F. So what is the complex conjugate? This is going to be, so we need to figure out what the C is. What will make this? I think then C is just equal to this, no? Because if it's the complex conjugate of C, we just take this down, take the complex conjugate of this, multiply it. I think it's commutative, so it's just turning into a number, right? So, okay, let's see if that's what he says.
Dx of C on F, complex conjugate, times G. But what is this? Well, C is just a number, so when we take its complex conjugate, we can just pull it out. So this is equal to the integral dx C complex conjugate F star G. But I'm now going to rewrite this using the awesome power of reordering multiplication as C star G. And I'm going to put parentheses around this because it seems like fun. So now we have this nice expression. The integral dx of F C adjoint G is equal to the C star G, C complex conjugate G. But notice that this must be true for all F. It's true for all, because any new assumption about what F and G are true for all F and G. And therefore, the adjoint of a complex number is its complex conjugate. Okay? And this is the basic strategy for determining the complex of the adjoint of any operator. We're going to play this exactly this sort of game. We'll put the adjoint in here, we'll use the definition of the adjoint, and then we'll do whatever machinations are necessary to rewrite this as some operator acting on the first vector. Cool? Questions? Okay, let's do it for a more interesting operator. So, by the way, to check at home, and I think this might be on your problem set, but I don't remember if it's on or not, so if it's not, check this for yourself. Check that the adjoint of the adjoint is equal to the operator itself. It's an easy thing to check. Okay, so next example. What is the adjoint of the operator driven with respect to x?
Okay. What is the adjoint of this? So let's remember our approach here. We are going like dx of f complex conjugate O dagger G equal to dx was it before? I think it was before. Yeah. I'm just gonna say because function complex operator doesn't make sense. Okay, so we got this. I'll put my hats on. G. So let's rewrite this. Dx f star All right. So so we've got this. This would just be df dx, complex conjugate of that, times g. How are we going to get this solution? Because if you take the derivative of f, it's not necessarily going to do anything to g. Let's watch.
Consider the operator, which is just derivative with respect to x. And I want to know what is the adjoint of this beast. Okay. So how do we do this? Same logic as before. Whatever the operator is, it's defined in the following way. Integral dx, f complex conjugate on dx dagger on g. This is equal to the integral dx of, integral dx of dx f complex conjugate on g. Now what we want is we want to turn this into an expression where the operator is acting on g, just our familiar operator ddx. So how do I get the ddx? Oh, by the way, so how do I get the ddx over here? We need to do two things. First, what's the complex conjugate of the derivative with respect to x of a complex function? MIT has indigestion. So this is integral dx, derivative with respect to x of f complex conjugate g.
Yeah.
And now
Okay.
I want this operator, I want derivative acting on g. That's the definition, right?
Right.
Because I want to know what is this
How do you
operator.
get the derivative over to the other
And so I'm
function?
going to do integration by parts.
Oh, geez, integration by
So
parts.
this is equal to the integral dx. When I integrate by parts, I get an f complex conjugate, and then an overall minus sign from the integration by parts minus f complex conjugate dx g. Was I telling you the truth or did I lie to you? Okay, keep thinking about that. And this is equal to, well, the integral of dx f complex conjugate of minus the derivative with respect to x acting on g. Everyone follow that?
All right, is equal to dx f star minus g.
But if you look at these equalities, dx adjoint acting on g is the same as minus dx acting on g. So this tells me that the adjoint of dx is equal to minus dx. Yeah.
Are you assuming that your surface term is vanished?
Thank you. I lied to you. So I assumed in this that my surface terms vanished. I did a variation by parts, and that leaves me with a total derivative, right? And that total derivative gives me a boundary term. Remember how integration by parts works. Integration by parts says the integral of a dxb is equal to the integral of, well, a dxb can be written as derivative with respect to x of ab minus, minus b derivative with respect to x of a, right? Because this is a prime b plus b prime a. Here we have a b prime, so we just subtract off the appropriate term. But this is a total derivative, so it only gives us a boundary term. So this integral is equal to
1.
The integral minus the integral over here. The integral and the derivative, because an integral is nothing but an antiderivative, the integral and the derivative cancel, leaving us with the boundary terms. And in this case, it's from our boundaries, which are minus infinity, plus infinity, minus infinity, and plus infinity. Now, this tells us something very important, and I'm not going to speak about this in detail, but I encourage the recitation instructors, who might happen to be here, to mention this in recitation, and I encourage you all to think about it. If I ask you, what is the adjoint of the derivative operator acting on the space of functions which are normalizable so that they vanish at infinity? What is the adjoint?
Well, that's going to be 1.
Acting on the space of functions which is normalizable at infinity? We just derived the answer because we assume that these surface terms vanish, right? Because our wave functions, f and g, vanish at infinity. They're normalizable. However, if I had asked you a slightly different question, if I had asked you what's the adjoint of the derivative operator acting on a different set of functions, the set of functions that don't necessarily vanish at infinity, including sinusoids that go off to infinity and don't vanish, is this the correct answer? No. This is not 3 terms. So the point I'm making here, first off, we're always in physics, we're always going to be talking about normalizable beasts. At the end of the day, the physical objects we care about are in a room, they're not off infinity. So everything is going to be normalizable. That is just how the world works. However, you've got to be careful in making these sorts of arguments and realize that when I ask you what is the derivative, what is the adjoint of this operator, I need to say something more precise. I need to say what's the adjoint of the derivative acting when this operator is understood as acting on some particular set of functions, acting on normalizable functions. Good. So anyway, leave that aside as something to ponder. Okay, but with that technical detail aside, as long as we're talking about normalizable functions, so these boundary terms from the integration by parts cancel, the adjoint of the derivative operator is minus the derivative operator. Cool? Okay, let's do another example. And we're going to do this. Yeah. So another example. Actually, no. I will do it here. Okay. So another example, which is 3. What's the adjoint of the position operator?
All right, let's see if I can do a little better this time. All right, so we've got dx f star of x hat adjoint g equal to dx x hat f plus conjugate of g. Now we know that the position operator is just throwing an x on there. So we're getting here, we got to do this one here. So we're getting dx xf plus conjugate g. And so I think we should be able to, this is just going to be a variable. So we should just be able to do, oops. We should just be able to plot this down and move it over here. So x at this should just be I don't know how you express the operator, but it should just be add. That's my guess.
Okay, take 2 minutes to do this on a piece of paper in front of you. I'm not going to call you, so you raise your hand. Okay, chat person next to you. Are you chatting about physics, right? Yeah, I guess. Okay, so how do we go about doing this? We go about solving this problem by using the definition of the adjoint. So what is x adjoint? It's that operator such that the following is true, such that the integral dx of f comes conjugate with x dagger acting on g is equal to the integral dx of what I get by taking the Comm's conjugate of t.
Oh, did I do that right? Yeah.
X and acting on F, and then integrating this against G. But now we can use the action of X and say that this is equal to the integral dx of X F complex conjugate G. But here's the nice thing: what is the complex conjugate of X times the complex function of F? X is real, right? Positions are real, so that's just X times the complex conjugate of F. So that was the essential move there.
Oh. Right, because X is real. X hat this is equal to X hat.
And now we can rewrite this as equal the integral of F complex conjugate xg. And now eyeballing this, X dagger is that operator which acts by acting by multiplying with X, little x. Therefore, the adjoint of the operator X is equal to the same operator. X is equal to its own adjoint.
Okay.
Okay? Cool. So we just learned a couple of nice things. So the first is, we're going to do this. Yeah, good. So we learned a couple of nice things. And I want to encode them in the following definition. Definition: an operator, which I will call O, whose adjoint is equal to O. So an operator whose adjoint is equal to itself is Hermitian. Okay. So an operator which is equal to its own adjoint is called Hermitian. And so I want to note a couple of nice examples of that. So note a number which is Hermitian is what? Real, right? An operator. We found an operator which is equal to its own adjoint. X dagger is equal to X. And what can you say about the eigenvalues of this operator? They're real. We use that in the proof actually. So this is real. I will call an operator real if it's Hermitian. And here's a fact, a mathematical fact, which is that any operator which is Hermitian has all real eigenvalues. So this is really almost stated as a theorem, but it's just a fact for us. O has all real eigenvalues. Okay. Yeah. Is it if it, no? It's not. If it's
Hermitian.
So if you have all real eigenvalues, it does not imply that you're Hermitian. However, if you have all real eigenvalues and you can be diagonalized, it does imply that. So let me give you an example. So consider the following operator. Rotations, we've done this many times. Rotation in real three-dimensional space of a vector around the vertical axis. Okay, it has one eigenvector, right, which is the vertical vector, and the eigenvalue is 1, so it's real, right? But that doesn't have to make it Hermitian, because there's another fact that we haven't got to yet with Hermitian operators, which is going to tell us that the Hermitian operator has as many eigenvectors as there are dimensions in the space. Okay, i.e. that the eigenvectors form a basis. But there's only one eigenvector for this guy, even though we're in a three-dimensional vector space. So this operator, rotation by an angle theta, is not Hermitian, even though it does have its only eigenvalue is in fact real. So it's not an only if. If you are Hermitian, your eigenvalues are all real. You'll prove this on a problem set. Yeah.
Are your eigenfunctions normal?
Not necessarily, but they can be made normal. We'll talk about this in more detail later. Okay. So if that's so, let's do a quick check. Last example, and I'm not actually going to go through this in detail. But what about P? What about the momentum operator? First off, do you think the momentum is real?
Momentum.
It sure would be nice, right? Because it's eigenvalues are the observable values of momentum.
Okay, let's try it again. I may have to switch to pencil for doing the problems. Okay, and what is the momentum operator? Momentum operator. I'm gonna have to go back to the notes. Where did I write down the operators? I think it's IH bar or something. IH bar. Where is it? Where did I write it down? Here we go. H over I with respect to x. So we know that this is equal to so let's go over it then. So dx, then we want h bar over I df dx conjugate g. Now, what can we do here to solve this? Complex conjugate, I believe, is to multiply it all by negative I? No? If we multiply this by, is it negative I? Or like flipping it? Is that how it works? If it's negative I, or sorry, if it's multiplied by, are we multiplying it by I? This is why I need to brush up on my complex conjugates. I want to say that it's I. All right, I'm going to just say that the complex conjugate is multiplying by negative I, but I'm going to learn soon whether that's true. I think, what is it, complex conjugate? Is it the complex conjugate is the imaginary part is negative, so it's the same number, but the imaginary part is negative, so it's not multiplied by I. So let's just, this is the imaginary part. So because there's only an imaginary part here, it's going to be negative h bar over I df dx. But we know from the derivative operator that the derivative for normalizable functions is going to be this negative derivative. So this should be equal to h bar over I. Hold on a sec. That's positive, and then this is times. I think we also have to take the complex conjugate of this, no? I'm over it, right? So I think it's equal to this by that reasoning, no?
And so the calculation will be real. Does that mean we should not necessarily label this check? So what is the adjoint of P? Well, this actually we can do very easily. And I'm not going to go through the library. I'm going to just go into the following. P is equal to h bar upon I, or sorry, I upon, h bar upon I, dx. Right? And this is an operator, and this is an operator. So what's the adjoint of this operator? Well, this under an adjoint gets a minus sign, right? It's itself up to a minus sign. So it's the derivative Hermite. No, it's in fact we call anti-Hermitian. Its adjoint is minus itself. Okay. What about I? What's its adjoint? Minus I. Sweet. So this has an adjoint picks up a minus, this has an adjoint picks up a minus, and the minuses cancel. P adjoint is P.
All right.
So P is in fact Hermitian. Okay. And here's a stronger physical fact. So now we see that each of the operators we built is x of P. Each of the operators we've looked at so far as Hermitian, those that correspond to physical observables. Here's a physical fact. All the observables you measure with sticks are real. And the corresponding statement is that all operators corresponding to observables, all operators must be Hermitian. So to the postulate that says observables are represented by operators should be adjoined the word Hermitian. Observables are represented in quantum mechanics by Hermitian operators, which are operators that have a number of nice properties, including they have all real eigenvalues. Cool? Okay. Questions? Yeah.
And so if it has to be Hermitian and not just have like real eigenvalues, does that mean the eigenvalues always equal in many cases?
Yeah, the eigenvectors will. Yeah. We're gonna. So this is connected to the fact we've already seen. If you take an arbitrary wave function, you can extend it and say with definite momentum, right? That's a superposition. You can also expand it as a set of, in the sense states with definite energy or a definite position. Anytime you have a Hermitian operator, its eigenvectors suffice to extend any function. Okay? They provide a basis for representing any function. Okay. So that's the end of the mathematical side. Let's get back to this physical point. So we defined this operator A and this other operator A dagger. And here's my question first. Is A Hermitian? No, that's Hermitian, but there's an I, that I will pick up a minus sign when we do the complex conjugation. Oh, look. So shows fortuitous that I call this A dagger, since this is equal to A dagger. Yeah? Okay, so this is the adjoint of A. So this tells you immediately something interesting. X and P are both observables. Does A correspond to an observable? Is it Hermitian? Every observable is associated to a Hermitian operator. This is not Hermitian, so A does not represent an observable operator. Okay, and
All right, I'm just gonna write a little break here.
Post notes on the webpage which gave us some lengthy discussion, or might be one of the solutions, some lengthy discussion of what it means for A and A dagger to not be observable. You'll get more discussion of that there. So, meanwhile, if A is not observable, it's not Hermitian. Does it have real eigenvalues? Well, here's an important thing. I said, if you're Hermitian, all the eigenvalues are real. If you're not Hermitian, that doesn't mean you can't have any real eigenvalues. Just as that I haven't guaranteed for you that all the eigenvalues are real. Okay, so what we'll discover towards the end of the course when we talk about something called coherent states is that, in fact, A does have a nice set of eigenvectors. They're very nice. They're great. We use them for lasers. Okay, they're very useful, and they're called coherent states. But their eigenvectors or their eigenvalues are not in general real. They're generically complex numbers. Okay, so are they things you can measure? Not directly. They're related to things you can measure, though, in some pretty nice ways. Okay. So why are we bothering with these guys if they're not observable? No. Yeah. Yeah, good. Excellent. That's really good. So two things about it. So one thing is this form for the energy operator is particularly simple. We see the 1/2. This was suggested from before, but it makes it obvious that E is Hermitian, and that may not be obvious to you guys, so let's just check. So here's something that was shown in the problem set. AB adjoint is equal to B adjoint A adjoint. The order matters. These are operators. And so if we take the adjoint of this, what's this going to give us? Well, we change the order. So it's going to be A dagger, and we take the dagger above the A dagger. So this is self-adjoint or Hermitian, so that's good. Of course, we already knew that because we could have written it in terms of X and P. But this is somehow simpler, and it in particular emphasizes the form of the recapitulates the form of the energy eigenvalues. So indeed, the form. Why else would we care about A dagger? Okay, now this is a good moment. Here's the second reason. So the first reason you care is the sort of structural similarity and the fact that it's sort of nicely Hermitian in a different way. Here's the key thing. Okay. A and A dagger satisfy the simplest commutation relation in the world. Well, the second simplest. The simplest is at 0 on the right-hand side, but the simplest not trivial commutation relation. A with A dagger is equal to so what is A dagger equal to? We just take the definition. Let's put it. So this is x over x naught plus IP over P naught.
Let's just do this real quick. Plus I P hat over P naught. And then we want to multiply it by x hat over x naught minus I P hat over P naught minus x hat over x. Yeah. It's not minus. All right, so what do we have here? I'm just going to do a brute force. I'm going to try to be fancy. So we have x hat, so squared. We have minus IP minus x this plus this. Those are going to cancel. So we're just going to get and negative I times I is negative 1 times negative 1. So this is going to be plus p hat over po squared. And then this is going to be minus positive x hat squared same situation minus this this should cancel, and then we get plus why do these not cancel out? This should be 0. Where are we getting? I must be screwing something up. Oh, the order of the operators matters, so I can't do what I'm doing. Because this is x times p. Hold on a sec, I can't cross out those terms. Forgetting I have operators here. So let me just add into the formula. Here we have minus I x hat p hat over x0 p0, and we have this is plus I p hat x hat over p0 x0, and then here we have minus, and then this is x hat I x hat p hat x0 p0, and then this is minus p hat x hat p0 x0. And then these are the commutator of this is IH bar. No, I think it's IH bar. So let's just convert these all to IH bar. So these all cancel, and then we get left with minus IH bar 0 P0 plus no, we can't do that because that's the commutator of those. It's not the IX bar. can I get rid of these so that these are the commutators? Because this plus, okay, so if I get xp minus px and px minus xp, I've got those two commutators, so I just have to substitute them out. So if I have I x0 p0, let's just do this. I have e hat x hat minus x hat p hat. And then I have same thing here, minus I 0 p0. Same thing, I think, no. I'm still getting them commuting to nothing. I'm missing something here. Must be forgetting a minus sign somewhere. This is probably plus because I'm slipped it around. No, but I got a minus sign here. Otherwise, it's the same or the opposite? No, it's opposite. So this has got to be. I think I flipped this around. Yeah, xp. All right, so this is xp over px. All right, and then what are these? This is the commutator of x and p. And this is the commutator of, oh, so this is the commutator of p and x. Wow, I need to get a pencil. And this is the commutator of x and p. So this was, what was this? This was IH bar. Let's go back to the notes. Where did we discuss commutators? I feel like it was after this. Oh, here we go. The operators. Where's the commutation of the operators? IH bar. This is reversed. Is it -1? It must be negative. All right. This is not a negative IH bar. Then we've got, this is -1 over x0, p0. And this is negative. Is it negative? Oh no, this one would be negative. This one would be positive. So this is negative. And that's 1 over this. And then this is plus 1 over this. We got to drop the h bars. So is it 2h bar over x0, p0? I feel like I've missed something. So I feel like I've definitely gotten something wrong here, but we'll just see what, I guess.
Comma, x over x naught minus I p over p naught. Hat, bracket. Good. So here there are going to be four. There are going to be four terms. There's x commutator x. What is that? What is the commutator of an operator with itself?
0.
0, because remember the definition of the commutator is a.
All right, these are 0. So
is AB minus BA. So A with A is equal to AA minus AA.
anyways, this is 0 because of that. Yeah, all right.
You have no options there. That's 0. So x with x is 0. P with P is 0. So the only terms that matter are the cross terms. We have an x with P. And notice that's going to be times and minus I with P naught and x naught. And then we have another term, which is P with x, which is I, P naught over x naught. So you change the order and you change the sign. But if you change the order of a commutator, you change the sign. So we can put them both in the same order. Well, let me just write this out. So this is I over x naught P naught. So this guy, so minus I over x naught P naught. But x naught P naught is equal to 2h bar, as we checked before. This was
right, 2h bar.
And
this is 1.
Plus I, again, over x naught P naught, which is 2h bar, P with x. This x with P is equal to I h bar. So the h bar cancels. The I gives me a plus 1. And P with x gives me minus I h bar. So the h bar and the minus I gives me a plus 1. Well, that's nice. This is equal to 1.
Okay, so I did get it right.
Therefore, A with a dagger is equal to 1. As advertised, that is about as simple as it gets. Notice a couple of other commutators that follow from this. A dagger with A is equal to
Minus 1.
Minus 1. We just changed the order, and that's just an overall minus sign. And A with A is what? 0. A dagger with A dagger?
0.
Good. Okay. So we are now going to use this commutation relation to totally crush the problem in submission. It's going to repeat for us like the Romans in front of physicals. It's going to be dramatic. Okay, so let's check. So let's combine the two things. So we have the first thing is that this form is simple. The second is that the commutator is simple. Let's combine these together and really build the system for what it's taught. To do that, I need 2 more commutators. And the lesson of this series of imaginations, it's very tempting to look at this and be like, why are you doing this? And the reason is, I want to encourage you to see the power of these commutation relations. They're telling you a tremendous amount about the system. So we're going through doing some relatively simple calculations. We're just computing commutators. We're following our nodes, and we're going to derive something awesome. So don't just bear with it. Learn from this. But there's something very useful and powerful about commutation relations. You'll see that at the end, but I'm going to hold on to this slight awkwardness right now that it's not totally obvious beforehand where this is going. So what is E with A?
All right, E with A is equal to, well, let's go back to the definition. This is A hat is, what was the energy operator? Energy operator in this system was, okay, so this is going to be, all right, so I'll just write right up here. E hat is equal to P hat squared over 2m plus m omega squared over 2x hat squared. And then our A hat is equal to x hat x0 plus I P hat over P0. Oh, all right, let's just figure this out. We've got this times this is going to be x minus I'm not going to fill that all out right now. Let's just solve this first part over here. So we have p hat squared x hat over 2m x0. We have plus I p hat cubed over 2m p0. We have m omega squared 2 x0 x hat cubed plus I m omega squared 2 p hat minus we have no, it's the opposite way, so it's going to be x hat p hat squared over 2m x0 plus this times this times this, so it's going to be x0, and then we have plus this is I p hat over 2m p0, and then we have this times this, so we have plus I p hat x hat squared this squared over 2p0. So let's eliminate the same terms. So m hat x this over this, these are going to cancel. I p hat 2m po these are going to cancel. xp this, hold on a sec, imw squared px squared 2p. So we're going to have this cancel, this cancel, this cancel with, oh, let's not cancel it. Let's just bracket it out. So we're going to have I m omega squared p0, and then it is x squared p hat minus p hat x hat squared. And then this one here, what's the other one here? This one here is going to be 1 over 2m x naught, and then this is going to be hat squared x hat minus x hat p hat squared. So these are commutator relationships of x hat squared and p hat. And this is p hat squared and x hat times this. Now, I don't know whether there's a simpler way of doing this. Because I know that p hat, x hat, I can just remove an x hat, right? So if I just, no, because they don't happen in the same order. Let me just see, because, yeah. All right, let me just write it down here. I m omega squared over 2p0 is, what is this? Oh boy, all right. We've got x hat, p hat minus p hat, x hat, x hat. So, is there any way I can get off a commutator relationship here? I don't know if there's any way I can break this down further. I think I'm missing some kind of like trick. Because this is the commutator, but I think these simplify somewhat, but I'm not quite sure how. I'll give it another like couple minutes and then I'm just going to move on with the lecture. Because I can't just kick one off, you know. Yeah, I'm stuck. All right, well, this is a good sign, though. I need to do some more work with the commutator relation so that I know kind of some of these methods. Let's see what he does and see. It's probably going to be way simpler than what I was doing.
Well, that's easy. It's the h bar omega a dagger a plus 1/2. So the 1/2, what's 1/2 commutator with an operator? 0, because any number commutes with an operator. 1/2 operator is operator 1/2. It's just a constant. That term is gone. So the only thing that's left over is h bar omega a dagger a with a.
Whoa. So I'm grabbing a different energy operator than he is. Okay, he's looking at something at the other board. Let's see what he's written down over here.
A dagger with a dagger. Okay. The Roman sign together and really they're telling you what is E?
Did I write down something? It says where did he start talking about A? Here. Oh, jeez. Okay, so I went through this whole big long thing because I'm using, we already did this for A. So, you know, this is the problem. I did this big math aside, and I should have gone back and checked my notes so that I knew what we were talking about more clearly. Okay. All right, let's go. Let's try it again with this new operator here. So we have E hat commuting with A is equal to, so that is going to be, I'm going to write it all out. I know he kind of simplifies it, but it's always helpful to just go slow when you don't understand something fully. So that's going to be, let's write this down, H bar omega A plus 1/2 this times A minus A times thought I had to sneeze there. All right. So this is H bar omega A T A A 1/2 A minus A I'll just put minus. You know, let's just move the H bar out over here. A. So 1/2 this goes over here. And then we have H omega A hat this minus so this is really a commutated with a this. I mean, you figure out what this is. Well, we know from doing the last one that A with A hat is A with A hat, A with A with Hermitian. What is adjoint? A adjoint. No, I'm still stuck. Okay, let's try it. See what it does.
With A, well, that's easy. It's the H bar omega A dagger A plus 1/2. So the 1/2, what's 1/2 commutator with an operator? 0, because any number commutes with an operator. 1/2 operator is operator 1/2. It's just a constant. That term is gone. So the only thing that's left over is H bar omega A dagger A with A. And then the H bar omega is just a constant. It's going to pull out no matter.
Okay, we did that. Yeah.
So I can just pull that
All right.
out.
That's where I'm at. So I've gotten so far. We're making progress.
Okay. So this is equal to H bar omega times A dagger A minus A dagger A. But this is equal to h bar omega. Well, that's a dagger a dagger a. You just pull out the a on the right. A dagger a.
Oh, right. Okay, yeah, because when we were doing it the last time, they had different things on each end, so we couldn't pull anything out. So that was the wrong way to solve it. But if we have this a, we can do a dagger a with a. Let's put our hats on. Oh, oops. Let me write it again. A hat, and we know this was already equal to 1, so this gives us AHW a hat. But what was a hat? There's got to be something here for this. A hat was equal to Is that our answer? Let's see.
Minus a dagger a. But that's equal to h bar omega. Well, a dagger with a is equal to a dagger with a minus 1 is
equal minus 1.
Minus
Oops.
h bar omega, and we have this a left over. A. So e with a is equal to minus a. Well, that's interesting. Now, the second commutator, I'm not going to do it. E with a dagger.
Wait.
Equal to.
Why did we lose the Why did we lose the h bar omega?
Well, let's just eyeball what's going to happen. There can be a dagger. So we're going to have a dagger minus a dagger a. So we're going to have a dagger in front and then a dagger. So all we're going to get is a sign, and it's going to be a dagger plus a dagger. Should have written that in the center. Everyone cool with that? Yeah. Oh, shoot, thank you. H bar omega.
Okay, good.
We would have misruled the galaxy. So, okay, good. Other questions? Okay. You haven't noticed yet, but we just won. We just totally solved the problem, and here's why. Once you see this, anytime you see this commutator, an operator with an a is equal to plus a times some constant. Anytime you see this, cheer. Okay? And here's why. Yeah, right, exactly. Now, so here's why. Here's why you should cheer. Because you no longer have to solve any problems. You no longer have to solve any differential equations. You can simply write down the problem, and let's see that you can just write down the answer. So suppose we already happen to have access. Now here in my sleeve, I have access to an eigenfunction of the energy operator. E on phi e is equal to E phi e. Suppose I have this guy. Cool? Check this out. Consider a new op state, psi, which is equal to a. Which one I want to do first? It doesn't really matter, but let's do a. Consider psi is equal to a on phi e. Okay? Consider this. What can you say about this state? Well, it's the state you get by taking this wave function and acting with a. Not terribly illuminating. However, e.
Assuming this is an operator.
Psi is equal to what? Maybe this has some nice property under acting with e. This is equal to e on a with phi e. Now this is tantalizing, because at this point, it's look, that e, it really wants to hit this phi, right? It just really wants to. There's an e, it wants to pull out, it'll be great. The problem is it's not there. There's an a in the way. And so at this point, we add 0, Okay, this is a very powerful technique. This is equal to EA minus E plus AE. Okay, phi E. Okay, but that has a nice expression. This is equal to EA minus AE, that's the commutator of E with A, plus A. Well, what's E acting on phi E? Well, actually, let me just leave this as AE. So what have we done here before we actually act? Phi E? What we've done is something called commuting an operator through. So what do I mean by commuting an operator through? If we have an operator A and an operator B and a state F, and I want A to act on F, I can always write this as, this is equal to the commutator of A with B plus BA at B on F. So this lets me act A on F directly without B, but I have to know what the commutator of these two operators is. So if I know what the commutator is, I can do this. I can simplify it. This is called, when one does this, when one takes AB and replaces it by the commutator of A with B plus BA, changing the order, the phrase that one uses is, I have commuted A through B. Okay? And commuting operators through each other is an extraordinarily useful tool, it's a useful technique. Now let's see why. So here, what's the commutator of E with A? Oh, we just did that. It's minus h bar omega A. And what's AE on phi E? What's E on phi E? E, right, exactly. Plus E A on phi. And now we're cooking with gas. Because this is equal to h minus h bar omega A plus EA. I'm going to pull out this common factor of E of A. Okay? So if I pull out that common factor of A plus E A phi E. And now I'm going to just slightly write this instead of E or minus h bar omega plus E, I'm going to write this as E minus h bar omega. I just literally changing the order of the algebra. E minus h bar omega. And what is AE? Psi. That was the original state we started with, psi. Well, that's cool. If I have a state with energy E, and I act on it with the operator A, I get a new state psi, which is also an eigenstate of the energy operator, but with a slightly different energy eigenvalue. The eigenvalue is now decreased by h bar omega. Cool?
What does this mean? Okay, we might have to revisit this.
And that is what we wanted. Let's explore the consequences of this. So, if we have a state with eigenvalue E, we have phi E, such that E on phi E is equal to E phi E. Then the state A phi E has eigenvalue, has energy, eigenvalue, E minus h bar omega. So I could call psi, I could just call this phi sub E minus h bar omega. It's an eigenvalue, eigenfunction of the energy operator, the eigenvalue E minus h bar omega. Agreed? Do I know that this is in fact properly normalized? No, because 12 times it would also be a perfectly good eigenfunction of the energy operator. So this is proportional to the properly normalized guy with some, at the moment, unknown constant coefficient normalization. Ever recall that? So now let's think about what this tells us. This tells us if we have a state phi E, which I will denote its energy by this level, then if I act on it with A phi E, I get another state where the energy, instead of being E, is equal to E minus h bar omega. So this distance in energy is h bar omega. Cool? Let me do it again. Let's act A on phi E. By exactly the same argument, if I make psi is equal to A on A phi E, A squared phi E, I get another state, again separated by h bar omega. E minus 2h bar omega. Turtles all the way down. slightly different calculation. So, okay, but before we do that, so I want to give A a name. Okay. A does something really cool. When you take the state phi e that has definite energy E, it's an energy eigenfunction, and you act on it with A, what happens? It lowers the energy by h bar omega. So I'm going to call A the lowering operator, because what it does is it takes a state with phi E, with energy eigenvalue E, to a state with energy E minus h bar omega. And I can just keep doing this as many times as I like and build a tower. Yes? Very good question. We'll hold on to that for a second. We'll come back to that in just a second. Okay. So this seems to build for me a ladder downwards. Remember that? But we could have done the same thing with a dagger. And how does this story change? What happens if we take a dagger instead of A? Well, let's go through every step here. So this is going to be E on a dagger. And then we have E, a dagger, E, a dagger. What's E with a dagger? A dagger. E with a dagger is equal to? Same thing, but with a plus. And again, psi, same thing, because the a dagger factors out. Yeah? So, we go down by acting with A, we go up by acting with a dagger. And again, the spacing is h bar omega. And we go up by acting with a dagger again. So A and a dagger are called the raising and lowering operators. A dagger, the raising operator. A dagger, phi E plus h bar omega. Okay. So what that is build a tower of states, an infinite tower of states. We're given a state we can walk up this ladder with a raising operator, and we can walk down it by lowering operator. So now I ask you the question: why is this ladder evenly spaced? There's one equation on the board that you can point to. Well, it's two technically. There are two equations on the board you can point to that suffice to immediately answer the question: why is the tower of energy eigenstates evenly spaced? What is that equation?
A?
Yeah, those commutators. These commutators are all we needed. We didn't need to know anything. We didn't even need to know what the potential was. Right? If I just told you there's an energy operator E and there's an operator A that you can build out of the observables of the system, so that you have this commutation relation, what do you immediately know? You immediately know that you get a tower of operators because you can act with A and raise the energy by a finite amount, which is the coefficient of that A in the commutator. Yeah? This didn't have to be the quantum mechanics of the harmonic oscillator at this point. We just needed this commutator relation, E with a dagger. And one of the totally awesome things is how often this shows up. If you take a bunch of electrons and you put them in a magnetic field, okay, a bunch of electrons, magnetic, very strong magnetic field, what you discover is the quantum mechanics of those guys has nothing to do with the harmonic oscillator on the face of it. Magnetic field, Lorentz force law, the whole thing. What you discover is there's an operator, which is usually called A, but it depends on which book you used, N or M or L. There's an operator that commutes with the energy operator in precisely this fashion, which tells you that the energy eigenstates
Are evenly.
in the ladder. They're called Landau levels. This turns out to be very useful. Any of you who are doing a UROC in the lab that has graphene or any material really with a magnetic field, but this matters. So this commutator encodes an enormous amount of the structure of the energy eigenvalues. And the trick for us was showing that we could write the harmonic oscillator energy operator in Commuting in this fashion. Yeah? So we're going to run into this structure over and over again. This operator commutes with this one, the same operator times a constant, that tells you I have a ladder. We're going to run into that over and over again. When we talk about Landau levels, we get there. When we talk about angular momentum, we'll get the same thing. When we talk about the harmonic oscillator, we'll get the same thing. Sorry, the hydrogen system, we'll get the same thing. Okay. So, second question. Does this ladder extend infinitely up? Yeah, why not? Can it extend infinitely down? Why?
Ground state.
Well, okay, people are saying ground state. Well, we know that from the root first calculation. But without the root first calculation, can this ladder extend infinitely down? Brilliant. Okay, good. And as we'll prove on the problem, you can't make the energy arbitrarily negative. But let me make that sharp. I don't want to appeal to something we haven't proved. proven. Let me show you that concretely. The energy expectation value in some state, in any state, right? The energy expectation value can be written as the integral of phi complex conjugate, let's say in state phi complex conjugate e phi. But I can write this as the integral, and let's say dx. Integral dx. Let's just put in what the energy operator looks like. So psi tilde, we can take the Fourier transform, right? The psi tilde of p squared upon 2m, oops, dp for the kinetic energy term, plus the integral, and now I'm using the harmonic oscillator, plus the integral dx of psi of x, norm squared, m omega squared upon 2x squared. Okay. A little bit of a quick move there, doing the Fourier transform for the momentum term and not doing the Fourier transform, but it's okay. They're separate integrals. I can do this. And the crucial thing here is this is positive definite. This is positive definite. Positive definite. Positive definite. All these terms are strictly positive. This must be greater than or equal to 0. It can never be negative. Yeah? So what that tells us is there must be a minimum E. There must be a minimum energy. And I will call it minimum E naught. Okay? We can't lower the tower forever. So what is that? How is this possible? How is it possible that, look, on the one hand, if we have a state, we can always build a lower energy state by acting with the lowering operator A. And yet this is telling me that I can't. There must be a last one where I can't lower it anymore. So what reaches out of the chalkboard and stops me from acting with A again? How can it possibly be true that A always lowers the eigenfunction, but there's a least one that can't be lowered any further? Non-normalizable is a good guess. Very good guess. Not the case. Because at this point, from this argument, we don't even use wave functions. That would be bad. Yes, exactly. So that would be bad, but that doesn't, I mean, that's just saying that there's an inconsistency here. So I'm going to come back to your answer non-normalizable. It's correct, but in a sneaky way. Here's the way it's sneaky. Consider a state, A, on phi, let's say this is the lowest state. Okay, the lowest possible state. It must be true that the resulting state is not phi minus h bar omega. There can't be any such state. And how can that be? That can be true if it's 0. So if the lowering operator acts on some state and gives me 0, well, okay, that's an eigenstate, but it's a stupid eigenstate. It's not normalizable. It can't be used to describe any real physical object, because where is it? Well, it's nowhere. The probability density, you can find it anywhere. This is nowhere. Nothing. 0. So the way that this tower terminates is by having a last state, which we'll call phi 0, such that lowering it gives me 0. Not the state called 0, which I would call this, but actually the function 0, which is not normalizable, which is not a good state. Okay? So there's a minimum E naught, and associated with that is a lowest energy eigenstate called the ground state. Now, can the energy get arbitrarily large? Sure, that's a positive definite thing, and this could get as large as you like. There's no problem with the energy eigenvalues getting arbitrarily large. We can just keep raising and raising and raising. I mentioned that because later on in the semester, we will find a system with exactly that commutation relation, precisely that commutation relation, where there will be a minimum and a maximum. Okay? So the commutation relation is a good start, but it doesn't tell you anything. We have to add in some physics, like the energy operator is bounded to low for the harmonic oscillator. Question? Yeah.
So you basically show that this ladder has to be some particular energy eigenstate that I can construct ladder. You know what? I can't construct other intersect ladders.
Yeah, that's an excellent question. So I remember vividly when I saw this lecture in 143A, and that question plagued me. And foolishly, I didn't ask it. So here's the question. The question is, look, you found a bunch of states. How do you know that's all of them? Okay? How do you know that's all of them? So let's think through that. That's a very good question. I'm not going to worry about normalization, but there's a discussion of normalization in the notes. How do we know that's all of them? So, yeah, that's a little bit tricky. So let's think through it. Imagine it's not all of them. In particular, what would that mean? In order for there to be more states than the ones that we've written down, there must be states that R naught on that tower, and how can we possibly, this thing's totally falling apart. How do we do that? How is that possible? So, there are two ways to do it. So here's my tower of states. Okay. There's my tower of states, and I'll call this one phi 0. Okay. And so I raise with a dagger, and I lower with a. So how can it be that I missed some states? Well, there are two ways to do it. One is there could be extra states that are in between, right? So let's say that there's one extra state that's in between these two. Okay, just imagine that's true. If there is such a state, by that commutation relation, there must be another tower, right? So there must be this state, and there must be this state, and there must be this state, and there must be this state. Yeah? Okay, so that's good so far, but what happens? Well, A on this guy gave me 0, right? So A on phi naught was 0, and this is going to be some phi tilde naught. Suppose that this tower ends. Okay. And now you have to ask the question, can there be two different states with two different energies with A naught? Can there be two different states that are annihilated by A naught? Well, let's check. What must be true of any state annihilated by A naught? Well, let's write the energy operator acting on that state. What's the energy of that state? Energy on phi 0 is equal to h bar omega. This is a very good question, so let's go through it. So it's equal to h bar omega times a dagger a plus 1/2 on phi 0. Okay, but what can you say about this? Well, a annihilates phi 0. It gives us 0. So in addition to a being called the lowering operator, it's also called the annihilation operator, because, I don't know, we're brutal and we're like species. So this is equal to h bar omega. This term kills phi 0, again, with a kill. You know, 1/2 left over, 1/2 h bar omega, phi 0. So the ground state, any state annihilated by A must have the same energy. Yeah? The only way you can be annihilated by A is if your energy is this. Cool? So what does it tell you about the second ladder of hidden states that we missed? It's got to be degenerate, right? It's got to have the same energies. Yeah? I drew that really badly, didn't I? Those are even space. So it's got to be degenerate. However, Martin proved for you the known theorem last time, right? He gave you my spread argument for the known theorem. In particular, one of the consequences of that is that in a system with ground states, in a system with potential that goes up, you can never have degeneracies in one dimension. We're not going to prove that carefully in here, but it's relatively easy to prove. In fact, if you come along, I'm sorry, I'll prove it for you. It takes 3 minutes, but I'm going to set them out for you. So, coming below the Wronskian. That's awesome. So, okay, so I leave it to you as an exercise to use the Wronskian to show that there cannot be degeneracies in one dimension, which is cool. The Wronskian for the differential equation, which is the energetic equation. So, there can be no degeneracies in one-dimensional potentials with bound states. So what we've just shown is that the only way that there can be extra states that we missed is if there's a tower with exactly identical energies all the way up. But if they have exactly identical energies, it's degenerate, we can prove that there can't be degeneracies in 1D. So can there be an extra tower state we missed? No. Can we have missed any states? No. Those are all the states there are. We've done it without ever solving a differential equation, just by using that commutation relation. Now at this point, it's very tempting to say like that was just sort of magical mystery stuff, but what we really did last time is very honest. We wrote down the differential equation, we found the solution, we got the wave functions. So, you know, Professor Adams, you just monkeyed around the chalkboard with commutators for a while, but what are the damn wave functions, right? So, we already have the answer. This is really quite nice. Last time we solved that differential equation, right? And we had to solve that differential equation many, many times, different levels, but now we have a very nice thing we can do. What's true of the ground state? Well, the ground state is annihilated by the lowering operator. So that means that A, acting on phi 0 of x, is equal to 0. But A has a nice expression, which, unfortunately I erased. Sorry about that. So A has a nice expression. A is equal to x over x naught plus I p over p naught. Right? And so if you write that out and multiply it by some appropriate constants, this differential equation, this becomes the following differential equation. Well, the x is just multiplied by x, and the p is take a derivative with respect to x multiplied by h bar upon I. And multiplying by I over h bar to get that equation, this gives us dx plus p over h bar x naught, whoops, p naught, sorry, that shouldn't be an I, that should be p naught, good, x on phi 0 is equal to 0. And you solved this last time when you did the asymptotic analysis, right? This is actually a ridiculously easy equation. It's a first-order differential equation. There's one normalization, or there's one integration constant. That's going to be the overall normalization. And so the form is completely fixed. First-order differential equation. So what's the solution of this guy? It's a Gaussian. And what's the width of that Gaussian? Well, look at p naught over h bar x naught P naught over h bar, well, we know that P naught times x naught is twice h bar, right? So if I multiply by x naught on the top and bottom, get 2 h bar. The h bars cancel. So this gives me 2 upon x naught squared. You remember I said it would be useful to remember that P naught times x naught is 2 h bar? It's useful. So it gives us this. And so the result is that phi naught is equal to, up to an overall normalization coefficient, e to the minus x squared over x naught squared. Solid. Okay. So there, we've solved that differential equation. It's the easiest, the second easiest differential equation. It's a first order differential equation with a linear term rather than a constant. We get a Gaussian. And now that we've got this guy, look, do you remember the third Hermite polynomial? Because, you know, if you want, we know that the third excited state is given by h3 times this Gaussian, right? Do you remember it off the top of your head? Here's how you solve what it is. How do we get phi 3? First off, how do we get phi 1? How do we get the next state in the ladder? How do we get the wave function? Raising operator. But what is the raising operator? Oh, it's the differential operator I take with, okay, but if I had a dagger, it's just going to change the sign here. So now how do I get phi 1? Phi 1 is equal to, up to some normalization, okay, dx minus 2 over x naught squared. X naught, phi 0. Cool? So now, do I have to solve a differential equation to get the higher states? No, I take derivatives and multiply by constants. Okay? So to get the third Hermite polynomial, what do? You do this 3 times. This is actually an extremely efficient way. It's related to something called the generating function. Extremely efficient way to write down the Hermite polynomials. They're the things that you get by acting on this with this operator as many times as you want. That is a nice formal definition of the Hermite polynomials. The upshot of all of this is the following. The upshot of all this is that we've derived that without ever solving the differential equation, the spectrum, just from that commutation relation, I cannot emphasize it strongly enough, just from the commutation relation, EA is minus A times a constant, and EA dagger is A dagger times a constant. The energy eigenstates come in a tower. You can move along this tower by raising with the raising operator, lowering with the lowering operator. You can construct the ground state by building that simple wave function, which is annihilated by the lowering operator. You can build all the other states by raising them, which is just taking derivatives instead of solving differential equations, which is hard. And all of this came from this commutation relation. And since we are going to see this over and over again, and you will see this depending on how far you take physics, you will see this in 805, you will see this in 806, you will see this in quantum field theory. This shows up everywhere. It's absolutely at the core of how we organize the degrees of freedom. This structure is something you should see and declare victory upon state. You should see what the meaning is there, know the answer, and write it down. Okay? In the next lecture, we're going to do a review, which is going to introduce a slightly more formal presentation of all of these ideas. That's not going to be material covered on the exam, but it's going to help you with the exam, which will be on Thursday. See you Tuesday.
All right. So this one, again, I was working it out myself. I took some pause breaks to work things out. I feel like I understand it a little bit better. Conceptually speaking, I mean, this operator stuff, the fact that the commutator and the commutator with the adjoint has this property, creates this, it's still, I think, a little bit conceptually muddled, but I don't feel nearly as on the kind of quantitative side as when they were doing the brute force strategy. So I'm probably going to go through both of them. I think this is like a pretty good opportunity for doing something like Feynman technique, even if it takes a little bit of time. But I'm going to stick to the original plan just because I don't like to get bogged down too much until I have some sense of progress. So I think we're okay right now. We're probably just going to, these were both sort of attempts at deriving the properties of this energy tower. This wasn't going to be, you know, it's not like understanding this derivation procedure is going to, I think, impact too much the knowledge of the next class. So I'm going to do the next lecture, and then we're going to kind of stop, do a little bit of assessment of where we're at, and then go from there.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT. at ocw.mit.edu.
Hi, everyone. I'm in a very good mood today. I'm having a baby, so that's kind of exciting. So if I just start giggling, you know why. In 6 months, if I'm weeping on the ground, you'll also know why. So today we're going to do two things. The first is we're going to maybe do, well, the first is review a little bit of practice for the exam we have on Thursday. So we play a little bit more about the exam. The exam, by the way, has been rescheduled to be in 6120, not in Walker Gym, so it's going to be the usual place. We're not moving. The reason I'm changing the format on this exam, in part to make it a little less of a burden, but also because I'm starting with the question of how to make the exam most useful. The purpose of an exam like this is not to get grades for you guys, although that's an incidental byproduct. The purpose is to give you some feedback on how you're doing, how you're a fan of the material that's involved, and also to help you sort of learn some of the things that you might not have mastered. So the way the exam is going to be structured is going to be about 50 minutes of short answer questions, a couple of very short computations, but mostly short answer questions on paper. We'll hand those back and we'll go over those questions in class afterwards. Okay, so it's a relatively low pressure exam, and it's mostly conceptual. People cover everything we've done through this last problem set. Today's the degree we get to the lecture part of today after question. Today's lecture will not be directly covered. However, it will be fair game for the next midterm, which will be more of a traditional midterm, and that's going to be So the structure today is I'm going to give you a whole bunch of clicker questions, so we should get clickers out. And those clicker questions are going to give you a sense for the level and scope of the exam. The exam will be a little harder than clicker questions, but not a whole lot. And the difference is just it's going to be on paper in front of you instead of clickered, and thus have to give you a little more room to do calculations on a piece of paper. Short calculations. And then after that, we'll come on to some something as a review, but also an introduction to the direct factorization that many of our textbooks use, but that we haven't introduced in the lecture so far. Okay, any questions before you get started? 41. Other questions? I think there will probably not be practice exam because of the shift in format. Today will basically be a practice exam. If I can get my work together and get you guys a practice exam of the right format, then maybe, but it wouldn't be all that useful. It is the problem. So watch what happens today. Yeah. I will post the questions from the yes. So it's 50 minutes short. It's not going to be a science lab. If you're not going to be racing, you get the. Because to my mind, part of the reason that we're designing the exam this way is that it's testing your conceptual understanding, which is the important thing. So yeah, it will be. All right, so let's get started with the clicker part of today. So, we're on channel 41. Okay.
Okay. So I really like the clicker questions. I like that they do this for this class. It's kind of a nice, break in the lecture here. So let's start with this one. Consider the eigenvalue equation, d squared over dx squared. So the second derivative of f of x is equal to some constant times f of x. How many of the following give an eigenfunction and a corresponding eigenvalue? So we're looking for basically eigenfunctions of the double derivative operator, I'm assuming here. So we know right away that number 4 can't be it. So let me just put these questions as numbered right here. No number right away that f of x equals x cubed cannot be an eigenfunction, because you do the double derivative of that and you get what? You get 3x. And so 3x is not a scaled version of x cubed, and so therefore number 4 is out. So we can right away eliminate B as a potential answer. Sine kx, well, you take the sine, and then you take the sine that gets you negative cosine, and then you take it again, and you get, I believe, sine, so it's kx squared. I might be missing a factor of -1. So, all right, at least if we do sine x, and then we take the second derivative of that, we get, is it negative cosine x? Let's just think about that for a second. Sine wave looks like this. So what's the positive derivative of this? This is at a maximum here. So this is plus cosine x, correct? Because it's positive here and the cosine is positive. Okay. And then we take the derivative of this and we get negative sine x. So we have -1. And then that's also true because the cosine is sloping down in at the 0 point. and the sign is going up at that point, so it's a negative. It's the inverse of the sign, so it looks like this instead. Again, remembering my my first year calculus information here. So if we do derivative of x twice, we're going to get out the k each time. So it is going to be squared, but it's going to be negative k squared. So so 1 is also not. So 1. So we know that 1. So I'll just put them here. So we know that this is not 1 because it's actually negative k squared is c is the eigenvalue, although that is an eigenfunction. We know this one is not just right off the bat. So now we got to look at these other ones. So the exponential of negative x is going to be 1 because if we have e to the negative x, and then we take, so this is just, let's just say this is y equals this, y prime is equal to negative e to the negative x, and then y double prime is going to be equal to e to the negative x. It's going to flip back again. So this one is okay, so we'll give a thumbs up for this one. And then number 3, e to the ikx. So e to the ikx. Well, again, we're going to drop down the ik. Again, we're going to drop down the ik. So this is going to be I times I is negative 1. So this is going to be negative k squared. Negative k squared is correct. So this is also correct. So we have 2. So my answer for this one is B.
So consider this eigenvalue equation f constant times x. How many of these are eigenfunctions with corresponding eigenvalue? Okay. About 10 seconds. Just wait your clicks. Okay, and so your whoops, sorry, I just put your responses on the first one. They're saved in memory, just put them on the screen. So the responses, here we go. That didn't work. Wow, we just totally screwed out that. Wow, that's so weird. Oh no, that didn't work. Where did it go? There it is. Whoa, this is all very confusing. Okay, so that was your response B and C, 63 and 38%. So let's go back to this. So quickly discuss this with your neighbor. Okay, and now I'm going to just do. Copy, that's fine. Okay, 5 seconds. Awesome. Okay, that's it. So the answer is D, and 99% of the all expect that. Just so it's look.
Okay.
Next question.
All right, so we got that one right. Next question: psi 1 of x of t, psi 2x of t are two solutions of the Schrodinger equation. Is a sum of x of t, a1 b1 xt also solution of the Schrodinger equation? Yes, that's just a superposition principle, unless I'm missing something nuanced here.
Psi 2 are two solutions of the is the sum of the coefficient also solution of the Schrodinger equation. So check now. Okay, this will see that. This is next like a1 will be a1. Because a1 will be a2. Thank you. Yeah, we see that. Yeah. Wow. Yeah. So Einstein said on the dice, and I'll re-reference that Scott doesn't listen to your clear question. Yeah. Okay, and you guys have effectively universally. The answer is A. Yes, the superposition principle.
Okay.
Okay. Next question is going to be for answer. Here we go. Consider infinite square wells with A.
Okay. Consider an infinite square well with the same with A, the ground state of the energy of a finite square well is going to be lower energy, higher energy, same energy. Well, I'm going to guess it's going to be lower energy, A. And the intuition there is that when we have an infinite well, these are hard barriers, so it has to hit 0 at these points. Whereas if we have a finite well, what's going to happen is we're going to have, these are going to be kind of diminishing exponentials. Here, it's not going to need to hit 0. It's just going to need to hit such that these are asymptotic to 0 at the end, so they're going to trail off a little. So that means that the effective wavelength is going to be slightly wider here, and slightly wider wavelength equals lower energy.
And the comparison with square well with the finite well is lower higher energy or under. 10 seconds, so anything for this? 5 seconds. Okay, and most of but I got those here. All right, let's try again. Are you other questions put your hand over for B2? 1. Okay, and the first progress. The gradients on the middle first. The second case you got less force cramming the particle into the box. It's squeezed less tightly. More physically, you see that there was an element on the outside, but that tells you the wave function didn't have to go to 0 at the ends. It should get small and not onto a dying exponential. Right? That's the qualitative analysis of the wave function. But meanwhile, what that tells you is it has to curve less inside in order. It doesn't have to get 0. It just has to get to a small value, where it matches to the decaying exponential. So the curvature is less, and the energy is less. Cool. Okay. Next question. What was the question on that? Okay. Good.
Okay. At t equals 0, the wave function for a particle in an infinite well of width a, blah, 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 is a sine squared, where a is a suitable normalization constant, which is falling true about the wave function that's at time t. I think we did this one before, no? It's not time independent, so we know that that's not true because sine squared is not going to be, is going to be a, it's a superposition of the energy eigenfunctions. Because there's a superposition of energy eigenfunctions, we do not have a stationary state. So we know it's not A. B, psi xt, a sine squared, blah, 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 where E is the energy of the electron. What are we looking at here? I mean, I don't think so. I don't think it's going to be that. Like, that's, what is that? Just that's just a phase term, right? Yeah, I don't think it's going to be that. So I haven't worked it out, but my intuition is that B is also wrong. A sine squared is where A is the nth stationary state of the electron. Yeah, I think it's D. It's going to be a big complicated mess of something, so I'm pretty sure it's D. We wouldn't do this one. I think we did this one in the last class. Cn blah, 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 where this is, yeah, I mean, it's got to be D.
Time 0 wave function infinite well with a sine squared, with normalization. What's the wave function something on T? Well, we're not even solve the problem, but that would pretty decent from all these guys. They're going to be from. Right, you got 5 seconds. Okay, BR, 50, correct. So, time for next week. Alright, the moments, go ahead and go again. Good, 5 more seconds, and then put in your phone book. Okay, that's it for now. So, what's the answer? D is the answer. A lot of people suss it out, so who wants to give an explanation for why it's D? Good, okay.
So, sine squared is not an eigenfunction.
Fantastic.
So, in some way, it has to be a summation of eigenfunctions. So, not even having to look at eigenfunctions are, then you want a summation in it, and if you do.
Really, okay, so I'm pretty specific. That's exactly correct in every step. So the first thing is, that wave function at 0, sine squared of x, is not the energy operator for the system. In fact, we computed the eigenfunctions for the energy operator in the infinite square well, and their signs, where they get a 0 at the ends. On the other hand, any function with satisfying boundary conditions, normalizable, 0 boundaries, is a superposition of energy eigenfunctions. And we use that to determine the time interval. We take that superposition and add on the phase, e to the minus I dt on each bar for each of the energy eigenfunctions. And in part B, we express that wave function as a superposition with the coefficient Cn determined from the overlap of our original function and the energy eigenfunctions. Ever recall that? So this is literally just a transcription of one of our postulates. Okay, questions? If you have any questions at all, ask them. This is the time to ask them. Yeah. Exactly. So the way you get Cn is by saying, look, I have my wave function, psi of x is equal to sum over n, Cn, phi n of x, where these phi n's are energy eigenfunctions. E phi n is equal to En phi n, right, of x. And we also know that the integral of phi n complex conjugate phi m is equal to delta mn. Right? This is the same from orthogonal and properly normalized. We also write this as equal to phi n phi m. And we can use this to determine the CNs. The CN is equal to the inner product of phi n with our wave function. This is equal to the integral dx phi star phi n star psi. This is equal to the integral dx sum over n of Cn phi n. But it's over n of Cn, we will have this integral. So first, we'll just see that's sum for n Cn integral phi n over phi n. And that's over n, which is 0 less n Cn with the orthonormal. So 0 less n Cn. So it's not less n Cn. This is Cn. So Cn is the overlap of wave function, but it will this allows us to take our function, sine squared, and express the coefficients in terms of overlap of our wave function sine squared with the wave function's sine. And that's exactly the expression you see below. Cn is the integral of sine squared over wave function.
All right.
Cool.
Let's go forward.
Other questions? Okay, great. Next problem. Come to me, computer.
The energy eigenstates psi n form an orthonormal set, meaning that the integral of psi the complex conjugate psi of m psi n dx is equal to delta mn. What is the value of psi m complex conjugate the sum of Cn dx? So this came up in the lecture before, this sort of delta m whatever notation, and it kind of went over my head. I wasn't sure quite what was meant by that. So orthonormal set, meaning that they're all at right angles to each other if we're thinking about vectors. So if these form an orthonormal set, meaning that these dx, what is the value of this? For each n. I'm not sure about this one. So let me just jot down the timestamp for this, because this is definitely, whether I get the right answer by guessing or not, this is definitely not something I fully understand. So I want to make sure I log that. Orthonormal. All right. Purely speculating, I'm going to guess A. But I'm going to put a question mark there to show that I'm not that confident.
Okay, good. The eigenstates phi n, which we usually call psi n, but there it is, form an orthonormal set, meaning integral of phi m star phi n is delta m n. What is the value of integral psi m against the sum Cn phi n? Okay, you got 5 seconds. Give you a little extra time because people are clicking away. Okay, you now have 7 seconds because time is not linear. Okay, so quickly discuss, because there's still some ambiguity here. Okay, that's all right. Right, and the answer is C. Yes.
C. Okay, so the answer is C. So I got this wrong. I need to understand this better. I don't know whether he's going to explain it.
Right, because in fact we just did that. Okay, then we have it on the actual exam. So here's the next question. Let the Hamiltonian on A dagger.
All right.
UN equals En plus H omega, that should be H bar, A dagger UN. What can you say about A dagger UN?
So this is, what was it? All right. If the Hamiltonian operator A hat UN is equal to E plus H bar UN, what can you say about A UN? And I also am not confident on this one.
Here, what we should probably say, what can one say? Because, you know, it's possible. Okay.
All right.
What can one say?
So where did we have this big H bar thing? That came up in the notes before, right? I recognize that, but I don't remember exactly what it was. So where did I write that down? I wrote down this here, but that was something different. Yeah, so I'm also not super confident on that, but my guess is that it is an energy eigenfunction, so I'm going to guess B, but I'm going to put a little question mark there as well.
Here the assumption, just to say that out loud, the assumption is that UN is an eigenfunction of the energy operator H with eigenvalue En. Okay, you got 5 seconds?
Oh, sorry, what did he say? Hold on a second.
Okay, then we're on the actual exam. So here's the next question. Let the Hamiltonian on A dagger UN equals En plus H omega, that should be H bar, A dagger UN. What can you say about A dagger UN? Here, what we should probably say, what can one say? Because, you know, it's possible. Okay, what can one say? Here the assumption, just to say that out loud, the assumption is that UN is an eigenfunction of the energy operator H with
UN is an eigenfunction. Yeah.
Eigenvalue En. Okay, you got 5 seconds?
Yeah, I don't know.
All right, we are at 50-50. So
Jeez,
discuss amongst
okay.
yourselves. All right. Now, you got an enter here. You want 5 guesses? You have 10 seconds to do so. This is a lot better. Okay, this is great. So this is one of those really satisfying moments. It's improved, but there's still some real temperature. So I would like to get one person to argue for B and one person to argue for C. Who wants to volunteer, please? Who's going to argue for B? Someone's going to argue for B. Come on. I'm not going to argue for B. I'm not going to argue for C either. That defeats the argument for C. I have to say this all the time. So who's going to argue for B? Okay, you argue for B. Who's going to argue for C? All right, yeah, that worked out well. Great. B.
So,
Argue for B. You can do it.
So I originally actually just took these like as a hand to this. So originally I didn't read the question, and I thought since you're acting a ladder operator on the eigenstate that you get proportionality constant times some eigenstate, so that's why it could potentially be but I just
It's not the best argument imaginable for B, but we'll take it. So thank you. So I put someone in an impossible position. So C.
So we can see just from the first line that this is clearly going to be a stationary energy state.
Excellent.
However, we can also see that it is a distinctly different energy from the state that again not use of that.
Excellent.
So I should see the same state.
Fantastic. That's exactly right. So let me walk through that. Let me say that out loud. So from the first line, it is clear that the object AUN is an eigenfunction of the energy operator, right? And it's got eigenvalue En plus H omega. So it is a stationary state. It's an eigenfunction of the energy operator. However, it is not the same one because it has a different eigenvalue. So if what it means to be the same energy eigenstate is it has the same eigenvalue. If it has a different energy eigenvalue, it is a different state, and they're orthogonal. We proved this before. Two states with different energy are orthogonal. So they don't even, not only are they not the same, they don't even have any overlap. Okay? So it is a stationary state, but it's not proportional with the state UN. It's an important one. Okay. Questions about that one before we move on to the next?
how did you know it's not proportional to state UN?
If it were proportional to the state UN, then then it would be some constant times un. That's what we mean by saying it's proportional. But then if we acted on it with the energy operator, what would the eigenvalue be? So let me say this again. Suppose I have a state un, which I know that if I act with the energy operator on it, or this is sometimes called h, un is equal to en un. Okay. If I act with e on alpha un, where alpha is a constant, what is this equal to? Alpha en un. Right? So the eigenvalue is the same. It's en. Right? Because if you divide through by out. So if you have the same state, meaning proportional to it, then we'll have the same eigenvalue. But this manifestly has a different eigenvalue. Cool? Awesome. Okay, other questions? Yeah.
So key to understanding this problem was that H is this energy operator.
What is the H operator?
Ah, good. Okay, so H is another name. So some books use H and some books use E. And the reason goes back to classical mechanics. There's an object called the Hamiltonian, which it's sort of like saying, I don't know, it's like saying like bread and ban. But they evoke different things, right? You say bread and you think like Dixie, and you say ban, and you think, oh, the me of some gorgeous baguette, right? Okay, it has a different feel. It has a different feel. So this evokes different things. If you look to a classical mechanic, the Hamiltonian is the generator of time translations. Now, we don't usually, that wasn't the classic way of thinking about the energy operator in, say Newton's time, okay? But it is how we think about energy now. So this is just terminology. For anyone who didn't get that, sorry about that. This is something that we've run across before that I should add.
Oh, okay.
So when you hear people say the Hamiltonian, that means the energy operator. The reason I say energy operator rather than saying Hamiltonian, which is a more common thing in the lingua franca of quantum mechanics, because I want to impress upon you that it is the energy. It's nothing else. It's not some straight piece. It's just energy. Okay. Other questions? Bread. Other questions? Okay. Next question. Which of these graphs shows the curvature of the wave function in a classically allowed region?
In a classically allowed region. A. Actually, no, this one. All right, we're on question 7 now. This is A, and the reason why is because this forms sine waves. Sine waves are what happens where you're allowed. Everything else is something different.
Okay, 5 seconds left. All right, fantastic. The answer is A, because the curvature has to be towards the axis. In the classically allowed region, the wave function is sinusoidal. It's oscillator. All right, and oops. And the partner of that question is, what about the classically disallowed region?
Classically disallowed region is B. Has to be growing or shrinking exponentials.
Okay, 5 seconds. Okay, awesome. And basically, everyone got this. The 3 questions. All right. Oh, yeah, sorry. No. No, that's a very good question. So C and D, actually, let me be a little more precise about this. It's a very reasonable question. So let me give you an answer. Suppose you saw a wave function that had the curvature structure of C. It was curved oscillatory over there and curved exponential over there on the right. What would you say about the potential relative to the energy? See it? Yeah, good. So on one side we're allowed, and on the other side we're disallowed. So if you saw a wave function that had that curvature structure, you immediately know that it was on the allowed region on the left, but then on the right it was disallowed, basically because it had curvature wave. So then if you saw a wave function, so for example, you never get a wave function that does this, and that's not true. Right? You do that. So this would be classically disallowed because it's curvature down. This would be classically allowed. So the potential for this is the energy. The potential could be 2. Okay, so things like this would lead to a wave function like this. Cool? Okay, that's a very good question. Sorry, I should have seen what graphing was giving. Okay. Other questions following on? No, I have a question before. And I just want to emphasize that you guys just ask questions when you're confused about someone else. You just the question of the question. Okay, have fun. Wave function. Sorry, the next question has somewhere.
Okay, a wave function psi of x has been expressed as a sum of energy eigenfunctions. Un of x is psi x is the sum of these energy eigenfunctions. Compared to the original set, the set of the numbers contains, well, we already did this one. So this one we know is C. I guessed it wrong yesterday because I thought that there was phase information that maybe was getting that, like, obviously that doesn't determine the energy, but would add up to it, but I was wrong. So I mean, we know it's C, but I still have to convince myself exactly why there's no phase information is getting lost.
The original wave function is a function of x, set of coefficients, C1 contains more or less determinant depends. All right, 5 seconds. right, and the answer is same information. Good questions? Something easy more. At the wave function is a constant. Then you write C on case and do. Okay. Yes.
Hold on a sec, sorry. Press two buttons at the same time. F and G are wave functions and C is a constant, and C dot FG is equal to, that's B. This is also one we did before, I think this is CC, because the first one gets complex conjugated. So I think this should be B, if I'm not doing something stupid here.
Okay, you've got about 5 seconds. Still have fluctuations here. All right. I'm surprised by this. All right, yeah, question. Oh, this is my reason for this. Sorry, thanks. We're going to need to okay. He has 30 as well. So it's okay, so and put your answers again. Good. All right, another 5 seconds. 1, 2, 3. Okay, and the answer is good. That complex conjugation right. Little thing like that can help you through trouble, especially as you notice on the problem side. When you're taking time dependence expectation values, getting that complex conjugation right is essential because you need to see interference terms, so that complex conjugation you will not get the right interference terms. Okay. Question? Oh, yeah, question from previous one. Thank you.
So, since the summation was a constant, yes. So, that would give you the probabilities of individual happenstance. So,
the norm squared gives you the probabilities. But if you know the coefficients, this is a good question. So, let me rephrase the question. So, the question is, look, in the previous question we said, look, our wave function phi, that's some function which we could draw. Right? So, I can represent this two ways. I can either draw it, or I can represent it as equal the sum over n of Cn phi n, where phi n are the known energy eigenfunctions. Right? And the question is, do the Cn contain the same information? So that was the question. And the point that's being asked about here is a very good question. The question is, look, we know what these CNs mean. What the CNs mean is the probability that you measure the energy, given that the state is signed, probability usually measure the energy En is equal to norm Cn squared. Right? And so the CNs tell you about probabilities. They don't tell you what the state is. They just tell you what probabilities they can measure a particular energy. Is that right? So how can they contain the same information? And there are two important things to say about this. First off, this is of course true. And this does give you the probability, and it probably comes from the norm squared, so the phase of Cn doesn't particularly matter for that. However,
the phase is in Cn, okay.
In a basis of energy eigenfunctions, in a basis of other functions. Is the same that if I know these Cn's, then I take C1 multiplied by phi1, C2 multiplied by phi2, add them all back up, and I get nothing other than its original function. So if I know the Cn's, I can just construct that original function explicitly. So this can't contain any more or any less information than the list of Cn's, as long as I know what basis I'm talking about. Okay, so here's the disturbing thing about that. When we say the wave function is the state of the system, it contains all knowledge you could possibly have access to, and not just knowledge that you could have access to, it contains all of the information of the state. And then we look at this and say, well, look, it doesn't give us something deterministic, it gives us something probabilistic. It tells us the probability distribution for measuring the various different energies. What does that immediately tell you since they're equivalent information? This guy tells you nothing more than probabilities. Remember, it doesn't tell you what energies you'll measure, it tells you the probabilities with which you'll measure energies. So they're the same thing. It's a very good question, and the sort of discomfort that that causes me is to read that same with the wave function is giving you probabilistic information about measurements.
And not just that you have wave function written as that wave function written as some. Yes. I just see since it's written that way, then you know what all the depends are and what all the possible answers are. And just I understand the information, but just written as excellent.
Okay, so let me turn this around. Let me phrase this slightly different. This is getting at the same point. If I give you a list of numbers, 1, 14, 12, does that tell you what function I'm talking about? No. I have to tell you that there are the expansion coefficients in, say, sine waves of a particular wavelength, or energy eigenfunctions of some particular energy operator. But if I give you a list of numbers, it doesn't tell you what function it is. I give you a list of numbers, and I have to tell you what basis I'm talking about. If you have the wave function, you don't need to know what basis you're talking about. The wave function is basis independent, right? It's just a function. In a few minutes, I'm going to come back and subvert what I just said. But so the wave function is just what the wave function is, and if I give you a list of numbers, they're only equivalent when you also know the wave function. So in order for these two things to be equivalent, it's important that you know what basis you're talking about. In particular, it's important that you know the energy eigenfunctions. Is that getting what's the distinction you're making? Okay, think more about it, and when the question becomes more sharp, ask. Okay, other questions? Yeah.
Yeah, I think you kind of covered what my question was, but for the future, if the question is phrased such that, like, you know the end, you know all the information, are we supposed to just infer that, see if we also know the formula?
Yeah, usually. I try on problem sensing exams to make that distinction clear, but that will generally get sued. Other questions? All right. I'm going to come back to this, but, well, I'm going to come back to this when we finish with the clicker questions. Okay, next question. In the simple harmonic oscillator, the eigenvalues, as we've just derived twice, are En is a bar n, or a bar times n plus 1/2 for an integer n. And a measurement of energy will always observe one of these values. That's from postulate 4. 3. What can we say about the expectation value of the energy in some arbitrary state?
The simple harmonic oscillator, the eigenvalues of the energy are this, and a measurement of energy will always observe one of these values. What can we say about the expectation of the energy? Well, it's not going to be A because it's not necessarily A because the expectation doesn't need to be a physically realizable state. It will never be one of the E. Well, again, if we I mean, presumably a physical state could correspond to just, it could be a stationary state that the ground energy, so the expectation would just be the ground energy. So B also seems to be wrong. C, it is sometimes one of the En, but only for a stationary state. It is sometimes one of the En, not necessarily for a stationary state. Something else. Given that they're evenly spaced, I imagine you could have a superposition of like ground 1, ground 2, so that the expectation is ground 3, but it's 3 different energies, so it's not a stationary state. So I'm gonna guess D for this. But maybe I'm missing some reason why it's C. Put a little question mark next to my thing.
All right, you got 5 seconds? Yes, sir. Complete chant. I think we just put you through a hardness box. So discuss.
I think this is D.
And okay, go ahead and start. Put in your modified response. All right, another 5 seconds or so. Okay, click. Okay, there's still a lot of disagreement here. So let's see. So who would like to argue for C? Who would like to argue for B? Go ahead.
Yeah. Okay. So I'm going to argue for the against C. So C suggests that we would measure the value of E and only for like let's say that it at rest. But given it can take the stationary state can consist of more than one
Okay, I'm not gonna listen to him.
Like the amount it has to be it's not like one year and but it has all to the amount.
So this, if I'm following your logic, so the statement, if I'm following your logic, goes down like this. Look, if we had the wave function, which was phi sub n times some phase, some ridiculous phase, let's say the phase is 1. If we had the wave function as phi sub n, what will the expectation value of the energy operator be in this state? En, right? Because it's the energy, it's the sum over all possible ends of En times the probability that we measure En. By definition. But this is equal to sum over n of En times the expansion coefficient of our wave function in the energy eigenstate basis, Cn squared. Now, what's the expansion coefficient in our energy eigenbasis here? It's 1 for a particular value of n and 0 for everything else. Right? So what will our answer be? It will be 0 for everything except 1 for a particular value En corresponding to little n. I should really call this m, so that dummy variables that we're summing over don't matter. So for this particular case, the expectation value of E is equal to En. Everyone cool with that? So it certainly can be En. But is this the only way to get En? No. So for example, suppose we have alpha, or phi 1 plus beta, phi 3. Okay, what will the answer be? Now, first off, in order to make this normalizable, what does beta have to be? It needs to be square root of 1 minus alpha norm squared. Right? Just so that they sum to 1 norm squared. So what I want to plot now, the expectation value of the energy as a function of alpha. When alpha is 0, what is the expectation value of the energy? E3. When alpha is 1, which can't be anything greater than 1, if alpha is 1, what is the expectation value of the energy? E1. And how does the expectation value of the energy vary between these two as a function of alpha? Well, it's smooth, right? And in particular, it's quadratic because it goes like the square of these coefficients. So So it's something smooth that does this, and has slope 0 at the end. Okay? And somewhere in between, it will hit E2. But there is not only is this not equal to E2, it doesn't even contain E2 as an element of the superposition. Right? So this is a counterexample to C. Verbal? This is an important point. Now, if I let the system, if I know that at some moment in time, the energy expectation value is this value, corresponding to some particular algebra, and I let the system evolve in time, how does that expectation value evolve in time?
Stays the same.
How does the expectation value of the energy change over time? It doesn't. The expectation value of energy is always time independent. Yeah? Does the expectation value of position change over time? In general, yes. When does it not change over time? In a stationary state. Right? So this is working through this is what's on your previous problem set as well as on your current problem set. Yeah.
So is this anything like conservation of energy where like the expectation value of energy needs to stay the same if there's nothing going on?
Excellent. It sort of sounds like that. We'll make a short version of that later. So you should have that tinkling in the back of your head like, oh, look, we have a time-independent potential, energy is conserved. That sounds kind of like the expectation value is constant, but we need to make that more precise. We'll find a precise version of that later this semester. But it's a very good intuition to have. Other questions? Okay. So the answer is D. And you guys are about 4 on that again. Oops. That was all right. 4. Okay, next one. This is a 3-step question.
Okay, observable A is, I'll just listen to him.
Well, and even I say psi 1 and psi 2 and phi 1 and phi 2 of A and B. And I can say A1, A2 and B1, B2. The answer is related in this linear fashion. I measure observable A and get the value of A1. What is the state immediately after that measure? What is the...
Oh, okay, so observable A, all right, observable B. The eigenstates are related by this complicated relation. Where are the phi's coming from? Oh, that's for observable B. Observable A is measured, and the value A1 is found. What is the state immediately after measurement? Well, immediately after measurement, it's going to be psi 1 because the system collapsed.
Wait. All right, 5 seconds. 2, 1, click away. Okay, great. So there's pretty strong agreement among y'all that the answer is A, and that is indeed the answer. Okay, questions? Okay, good. So a slightly less obvious one.
Okay, immediately after the measurement of A, the observable B is measured. What is the probability that B1 will be found? Ooh, where are we here? B1. Okay. So B1 corresponds to, oh boy. So we know that it is, we know that it is in the state psi 1, and then we measure B1. That doesn't work. What am I missing here? There's a probability that D1 will be found. You know, I don't know. I'm going to guess. I feel like it's going to be C, but maybe I'm not sure of that. I'm just going to put C question mark here.
Immediately after this measurement of A, the observable B is measured. What's the probability that B1 is found? Well, there's sort of measly initial transients there. I can use this. I can use the first couple of seconds as a random number generator.
Are we 2 or no? Oh, geez, 4 over there? No. Was it 4 or 13?
Okay, that's it. And there's actually a third of you disagree with the correct answer. So I'm going to invite you to chat. Answers. 15 more seconds. 1 second. Okay, nice, excellent. You guys went from about 65% to 90%. That was great. The answer is E.
Oh, it is E. Okay. And then the reason is because we're in psi 1, and so we have 2 over root 13 is this related to this eigenstate. So the probability of that is going to be this squared, which is equal to 4 over 13.
It's the norm squared of the coefficient of the eigenvalue or eigenfunction corresponding to d1 in the original state, which was psi. Okay. Now imagine, on the other hand, that the graduating measurement failed to in fact measure the interval b.
Failed to measure b, but instead measured a for a second time. What is the probability of the second measurement will be 1? Well, this one's E. This one is B1.
It was that A. But instead of A, again, what's the probability that the second measurement will yield A1? Trust me, there's so many ways. They got the package wrong. They did wrong measurement. Sorry, thank you. No, very much. He accidentally measured B instead of A. I mean, A instead of B. Accidentally A. See how easy it is to make a mistake? He accidentally measured A instead of B. I think that was intentional. Okay, so, and we get almost all unanimity. The answer is B. Yes, question. Great question. Let's just assume it's instantaneous. He's sloppy, but he's very quick. Okay, next question. The system is in a state which is a linear superposition of n equals 1 and n equals 2 energy eigenstates. Blah. What's the probability that measurement of the energy will yield the first energy argument?
It's equal to 1/2. We do have interference terms, right? I still think it's 1/2. Right, I'm gonna go 15 here.
Another 5 seconds. 2, 3, 4, 5. Great, you guys totally agree. The answer is C.
Okay.
Great. Okay, that's it. That's it for the clicker questions for today. So here's the thing I want to emphasize. The first is that these are totally conceptual. They did not involve any computations, and yet they're not trivial. Some of them got 50% consistently across the class. So it's not just the calculations that are hard. Just thinking through the basic premises, the basic postulates is really essential at this point. It's more important than the computation. Yeah. I will post these. Okay. Any questions remaining from after this little? Oh shoot! I missed out on a whole opportunity. I'll do it next time. Cool. Any other questions before we move on to the lecture part? Oh, you totally calculate. Yeah, you totally have to wait. Okay. Any other questions? Yeah.
Have you ever had a function odd, or just like these like down progressive?
Well, that's a very good question. So the question is, can you ever have a potential function that is odd? So for example, you're actually asking 2 questions. Let me disentangle it. So one question is, can I have an energy and then a potential function which is odd and linear, right? So it just ramps all the way down. So does that seem physical? Is the energy bounded from below? No. Okay. Well, that's not a terribly good criterion because it's not bounded from below for the Coulomb potential either, right? But in the case of the Coulomb potential, it's not bounded from below in a little tiny region, right? Not a huge swath. So we're going to need a better definition of this. But the short answer to this one is no. This is not good. Okay. On the other hand, it's not the oddness that's bad. It's that the energy is continuing to be unbounded from below. And here's what, so we can be more precise than saying it's not happy. What is it? What's important for an observable? What's important for an observable? The operator corresponding to an observable in quantum mechanics. What property must that operator have? It has to be Hermitian, right? And if you that implies real eigenvalues, it implies that there's basis of its eigenfunctions, all these nice things. What we will find is that the Coulomb potential, a hydrogen potential, gives us a nice Hermitian energy operator. We'll prove that the energy operator is self-adjoint on problems. However, this guy will not. Okay, so we're going to have one that is not bounded from below. So while there's a sense in which it's Hermitian, there's not a good sense in which it's got problems. So that's a more technical detail. However, there's a second part of your question, which is you could have been asking, look, you have a potential that's odd, but let's leave this on be diverging at infinity. So for example, you have a potential that does this, so that it's odd, but it's bounded. And that's fine. Nothing wrong with that. So odd isn't the problem. The problem is certain ways of diverging. Yeah.
So like, does that mean, so what would happen in the case where you did have some kind of linear potential get a uniform electric field and something was moving? Is that like just, is the problem that potential technically isn't like a physical potential because it doesn't go away? Or?
Yeah, well, how would you ever build a linear potential, right? So the question here, look, I'm not going to build a linear potential. turn a uniform electric field, and the electric field is the gradient of the electrostatic potential. So that means the electrostatic potential is linear, and potential energy of a charged particle with charge Q in an electrostatic potential is Q times the electrostatic potential. So the potential energy for that charged particle is a linear function. So how do I build this thing? Well, I take two capacitor plates and dump some charge on this one, the opposite charge on this guy, and I build up a linear potential. Well, yeah, exactly. So that's the problem. So can I make this linear over an arbitrarily large domain? No, I need an arbitrarily large amount of charge, and I need to push them apart from each other arbitrarily far, which takes an arbitrarily large amount of work. That's not terribly physical, right? Your arms are only so big. So at the end of the day, what was going to discover that the pathology that showed potential is like, Hamiltonian is not something we can compactly supported. Space common supported out to function. And okay, that's going to always be some mathematical version of your arms are only so big. You can't need from large apparatus like this. So yes, you're exactly right. It is not physical. Is it a mathematical problem? Okay, analyze? Yes. Well, can write a dissertation on the singularity structure of these differential equations. But that dissertation would never be read by a physicist. Another question. Yes. Excellent question. No. So here's what you can do. Suppose I have a bunch of energy eigenstates. I have some potential, some crazy. This is a potential. It's a crazy potential, right? And it has a definite energy eigenstate. As we've shown in 1D, we don't, as I mentioned in proved in office hour, we can't find degenerate eigenfunctions in one-dimensional potential. So they're not degenerate states, but find this part for states, for wave functions that converge to zero infinity for bound states. So we can always construct an operator, which I will simply define in this way. A, and just for flourish, I will put a dagger on it, which does the following. A dagger is defined as the operator that maps phi n to phi n plus 1. Okay? So what's the rule? It takes this state to this state, this state to this state, this state to this state. And since we can extend, since these are a basis, then that's always how this acts on an arbitrary function, because it acts on the superposition as acting on each term. So we can define it in this way. But here's the question. What does it mean for the raising operator to be the raising operator? It wasn't that it lifted the raising operator. That's not what started out the whole machinery. Where the raising operator got its juice was from this computation relation, A dagger, with E was equal to H bar omega, A dagger. Right? So can we build an operator, A dagger, that raises states and commutes with the energy operator in this fashion? No, that depends on the energy operator. This is not a general property. This is not always something we can do. Okay? If we could, then that energy operator would have evenly spaced energy eigenfunctions. On the other hand, it's not like it's never useful. So consider the following example. I think this was a concept. I don't remember, so let me just say it. Consider if we write A dagger A is equal to N, right? Then the commutation relation for this, so the energy operator for the Coulomb oscillator was equal to H bar omega N plus 1 half. That's what we derived last time. If we define A dagger A as N, then the commutator of N with A dagger is A dagger. And the commutator of N with A is equal to minus A. Suppose the Hamiltonian, or suppose the energy operator, sorry, the French. Suppose the energy operator is equal to H bar omega N plus N cubed. Okay. Does the raising operator commute with the energy operator to give you A dagger again? No, because it's going to give you commutes to give you an A dagger. Commutes with this guy to give you, well, a constant times N squared A dagger. Which is a slightly funny beast. So this doesn't have the same computation relation. On the other hand, we know how to build the eigenfunctions of the N operator because they live in a tower by this algebra, by this commutator relation. They live in a tower. So I can build the eigenfunctions of N. And then I can take those eigenfunctions and then act on them with E, and we'll discover that they're also eigenfunctions of E. Because E acting on them is just N and Q acting on the eigenfunctions of N. So the states with definite N are still eigenfunctions of energy operator, but they're not evenly spaced. Now, can every potential be written in terms of this N operator? So I leave that to you as an exercise. The answer is no. Try it. Yeah, exactly. So there's always something you formally define in this fashion. It's not always useful to you because it doesn't always commute with the energy operator. It's a nice way, right? So now you can ask, are there thing properties that are? I thought there's something called the supersymmetric method in 1D quantum mechanics. But that's sort of beyond the scope. Come to my office hours and ask me this question again. This is a miracle of a harmonic oscillator. Other questions? Yeah.
So to construct the ground state, we use the condition that A phi 0 is 0. Yes. Did we how did we compose? Did we demand that physical ground state had to be 0?
Yes, we did. So that's the question. So the question is this. When we constructed using the operator method for the harmonic oscillator, when we constructed the ground state, we said the ground state, phi 0, is that state which is annihilated by the lowering operator. A phi 0 is equal to 0. So where did that come from? Were we forced into that for physical reasons, for mathematical reasons? What was the reason? So this was very important, so let's go through it slowly. So remember the step that came immediately before this step. Immediately before this step, we said, look, the expectation value of energy can always be written as a strictly positive thing. It's equal to the integral, and you should derive this for yourself. I didn't derive it. This is a good thing to derive for yourself. It takes only a couple of steps. Integral over momentum of psi tilde of p before you transform 1 squared. This is the probability that you have given the state psi. This is the probability density that you have momentum p, p squared 1 2n, plus the integral dx psi of x, norm squared, and omega squared 1 2 x squared. This is the probability that you're at position x, given the wave function x. It's the immense value of potential. Now this is a strictly positive quantity, as is this. Strictly positive, as is this. That is a plus. This quantity must always be greater than or equal to 0. Correct? However, we derive from the operator relations that if we take a wave function, phi sub e, and we come up with the lowering operator a, this defines a new state, which up to some normalization is an eigenfunction of the energy operator with energy e minus h bar omega. And we show this by showing that the energy eigenfunction acting on this gives exactly this coefficient times this back. It's an eigenfunction. We just showed explicitly it's an eigenfunction. So this suggests that if you have a state with energy E, you can also build a state with energy E minus h power omega. And thus we can repeat E minus 2h power omega, and this dribbles all the way down. The problem is, for any finite value of E, eventually this tower will get negative, here's 0. But the energy expectation value cannot be less than 0. It's got to be strictly greater than 0. But if we were in this energy eigenstate, and we measure the expectation value of energy, this is the value we would get, which would be negative. Oops, that's a 2. So something is amiss. How can this possibly make sense? And the answer we came up with was, well, look, it's inescapable that acting with A on phi gives us something that's an eigenfunction of the energy. However, it's possible that this function happens to be the 0 function. Not 0 energy, just 0. Not a function. Is 0 normalizable? No, the integral of 0 squared is 0. No coefficient times that is a finite number. It's 1. So the only way, so what must happen? At some point, we can't lower anymore. But we can always act with A. The grace try to lower. The only out is if when we lower one particular argument, call phi 0. The only out is if we try to lower phi 0, we don't get another state, which we assume we did here. We don't get another state, then we just get 0. We get no state. Not energy 0, it's 0. The function is 0. Everything vanished. This does not describe the configuration of a part. Probably if the integral is 0. That's bad. So in order for the tower to end, in order for the energy to be bounded from below, as the potential is, we need that there's a lowest state in the tower. That is your question? Great. Yeah. Very good question. You're going to show this on a problem set if you haven't already. I thought you did, but maybe not. The energy eigenfunctions for can only for potentials with only bound states can always be expressed as purely real or purely imaginary. You can always decompose in terms of purely real or purely imaginary. Proving that will be a problem on one of your problem sets, but for the moment, let me just say that yes, you can always show that the energy eigenfunctions for 1D potential can always be expressed as purely real. I need that bound state condition. We'll see later, of course. Yeah.
So we lowered energy phi naught. Yes. The next energy is 0, right? Yes. Isn't this supposed to mean that the phi naught is h omega, not h omega?
H omega, sorry. No. This sorry. No. Good. So what this says is, given some state with energy E, when we lower, we get h power omega less. That's essentially what E is. Good. Other questions? Yeah.
Just to expand on that, so like if you get the 0 function, that doesn't actually correspond to any energy eigenvalue. Correct. Let alone 0, right?
Correct.
So you just say any.
Correct. 0. The function 0 is an eigenfunction of every operator. But it's a stupid eigenfunction of every operator. In particular, it has nothing to do with the states we're interested in. We are interested in normalizable states. Right? And that's not a normalizable state. You can't multiply any finite coefficient and get 1. Okay. So, quick, yeah. One last question.
Maybe a silly question, but does that mean that the other particle that has 0 and the particle that doesn't exist?
We need to add more words. So the question is, does that mean that the only particle that can really have 0 energy is some imaginary particle that doesn't exist? First off, imaginary particles may. You should have seen that. I mean, right. Okay. So I need to say 2 things about this. So there's a technical complaint that make a question. So the very first question, they need to make all the same. And the second is one physical answer. So the technical complaint is, what do you mean by 0 energy? Do you ever measure energy directly? You measure energy differences. Right? So relative to what? We have to decide relative to what. So for example, in the harmonic oscillator, what we mean when we say the ground state energy is not 0 is if we draw the potential and we call the minimum of the potential E is 0, classically E is 0, then what we discover is that the energy of the quantum mechanical ground state is 1/2 h omega. Right? Above 0. Yeah. So is there any state of the harmonic oscillator with energy 0? No. Okay. Now, if we have a free particle, is there a configuration with energy 0? Well, that's an interesting question. So, what are the eigenstates? E to the I kx. Okay. When the energy is 0, so and the energy is because it's just p squared mod 2, which is h squared k squared mod 2. The energy is h squared k squared mod 2 for a free particle, no potential. And by 0, we mean the asymptotic energy equals 0. With energy 0. This is a little subtle because if we take the energy 0, what must it be? 0. Okay, great. So what's the wave function? Constant. Is that normalizable? Not so much. So can you build a wave packet with energy 0? Sorry, we must see that. Can you put a single particle in state with energy 0? No, that would not seem to be possible because that would be a non-normalizable state. What should we say? We deal with these exponentials all the time. You know how to deal with that. We don't use a single wave, plane wave. We use a wave packet with some width, right? So I can build a wave packet with some average width, but will that average width ever have expectation value of k equals 0? No, because it will always have contributions from k not equal 0, so that it's localized. So that it's spatially localized. So can you build a normalizable state with energy 0? No, not in this case either. So there's a particular thing. You need to talk about what we need relative to what. That was my question. The second, you ever have an energy eigenstate which is at a minimum potential, that's also 0. That's also no. You'll actually prove that on the problem. Okay. So with all that said, we have here, that's also 15 minutes for a 14-day lecture. So can I do this fast? No, I'm kidding. I won't do that too. So I want to instead of going through, so this was not directly relevant for the exam, and it's also this can come a little bit later. So let me just let me show you a couple of quick things. So the notes are posted online. Look at them. I'll go over them again in the future. What do I want to do? So I want to introduce you 2 ideas. One is documentation. And this is harkening back to the basics of vector spaces. And the second is I want to tell you something about what the commutator means. So first off, let me ask you guys a question. How can use? Okay, I have one more vector question.
Suppose two observables commute, A operator, B operator equals 0 is the standard deviation of A times B 0 or non-zero. Ooh, this is a tricky one. I actually don't know this one. All right, let's think about it. Well, I'm going to say non-zero because standard deviation is always positive. And if we did, let's say, A with itself, so let's say we just have the position function with itself, that would commute to 0. But yet we would have this not being 0. So I'm going to go with B. But let's see if that's right.
Can you go and start clicking now? Okay, so at the moment, let me give 3 more seconds. 1, 2, 3. Okay, this is awesome. You guys are totally at chance. You have even probability distribution across the group. So because we haven't actually introduced this idea yet in 804, so let me quickly talk you through this. Okay, so yeah, I'll leave it off. So let me quickly talk you through this. And this is important. This is going to give you some intuition for what uncertainty means, and it's also going to give you some intuition for what the commutator means. Okay, so this is a little more experience, a little more practice with operators, and we'll pick up on the direct notation and everything I think next time because I just want to get through this physics. So consider 2 operators, A and B. So A and B are my 2 operators. They have hats. He has a top hat. So we have, you gotta make this up a little more lighthearted. So we have 2 operators, A and B. And I want to ask, is it possible for there to be a function phi little a little b, which is simultaneously an eigenfunction of A and an eigenfunction of B? So now this is a pure math question. Given 2 operators, A and B, can you build a function which is simultaneously an eigenfunction of A and an eigenfunction of B? I will call this phi sub AB.
Yes.
Oh, why not? Okay, so phi sub AB has this property. A on phi AB is equal to A phi B. Why not? And B on phi AB is equal to B on phi B. You can tell me I have now created this object. What, from the existence of this state, what can you deduce about the operators A and B? And if you've already seen this before, that's cheating, so don't raise your hand. But if you haven't seen this before, just think through what does this tell you about the operators A and B? Great, that's a nice guess. I like that guess. So let's check. Okay, so what would it mean for the commutator of A and B to be 0? So AB is so this is equal to AB minus BA. And what the commutator does is it takes 2 operators and it gives you a new operator called bracket AB. Sometimes it's useful to call it C for commutator. So it gives you a new operator. Given 2 operators, you build a new operator. And saying that this is so good, and suppose now that we have a common eigenfunction of A and B. What does that tell you? Well, let's take the commutator A and B, and let's make it an act on phi sub AB on this common eigenstate. So what is this equal to? This is equal to AB minus BA phi B, which I can write as AB phi B minus BA phi B by linearity, by addition, really. Okay, but B acting on phi B gives me by hypothesis little b phi B, and then A acting on a constant times phi B gives me little a times that constant. Okay, minus, now here A acting on phi B gives me little a phi B, and then B acting on constant times phi B gives me little b. And so now I can join these together. This is equal to AB little AB minus BA phi B. But little a little b are numbers. If you take 7 times 5 and 5 times 7 and you subtract them, what do you get? 0. So in order for A and B to share a single eigenfunction phi AB, what must be true of their commutator?
Commutator must be 0.
It must have a non-zero kernel. Exactly. The commutator must annihilate that particular function, that common eigenfunction. Okay. Does it tell you that it kills every eigenfunction? No. But it must, at the very least, annihilate the shared eigenfunction. True? Consider 2 operators of the following form. Consider 2 operators whose commutator, A, B, is equal to the identity times the constant. Okay? Do these operators share any common eigenfunctions?
Yeah, they can't. Sure.
They can't, because the commutator, the identity, doesn't annihilate any wave functions. Any function. Nothing is 0 when acted upon by the identity. That's the definition of the identity. Right? The identity takes any function, gives it that function back. Cool? Do A and B share any common eigenfunctions? Now let's think about what that means in terms of observables. Observables are represented by operators. What are the eigenfunctions? What is the meaning of the eigenfunctions of those operators? It corresponds to the state with a definite value of that observable, and the value is the corresponding eigenvalue. Yeah. So the eigenfunction of an operator, of an observable operator, is a possible state with a definite value of that operator. If I tell you that I have a state which is an energetic function, then that means it is a state with a definite value of the energy. If I measure that energy, I know exactly what I would get. Cool? If these are two observables, if A and B are two observables, and their commutator is proportional to the identity, is it possible that there is a state with a definite value of A and a definite value of B simultaneously?
No.
No, because the state with the definite value of A would be an eigenfunction of A, and the state with the definite value of B would be an eigenfunction of B. And there are no common states, no common eigenfunctions of A and B, because the commutator never kills the state. It has no zeros. What is the commutator of X and P? With this memory, IH bar. Now, when we write H bar, this is not really a number. That's a number. What's the operator? The identity. Are there any states which are simultaneously eigenfunctions of X, the operator X, and eigenfunctions of P? Are there any states that have a definite position and a definite momentum simultaneously? Is that because we're ignorant? Are we ignorant? Yes. Okay, go. So it is not. It is because.
Oh, so this isn't true. So okay.
Forbid the existence of a state with a definite value of X and with a definite value of P simultaneously. It's either here or there or both or neither. Okay. So this tells us something very lovely. This tells us that if we're in a state with a definite value of X, what must be true of our uncertainty in the value of P?
Must be non-zero.
Be zero. Because if it were zero for uncertainty in the knowledge P, we're zero. That would be P would have definite value P. So if delta X is zero, delta P cannot be zero, for sure. Now, how big does it have to be? Could it be arbitrarily small? So here's a commutation relation. You will prove the following relation later on in the course. What I want to tell you now is I want to give you some intuition for what the commutator is, what it means, what the physics of it is. If I take two operators, A and B, with which have a commutator, which is a constant times the identity, then the uncertainty in any state, psi, of A, times the uncertainty in the state psi, same state psi of B, must be greater than or equal to 1/2 the absolute value of the expectation value of the commutator, that's an amazing set of symbols, of A with B. Square root. I'm going to take square root. So the easier way to, let's see, AB, let's just make sure I'm getting this right. Commutator being B, it's, no, there's no square root, sorry. You're already messing with me. Expectation value of A and B, of A, of B, for, yes, good. Okay, so in MTW, this expectation value should be taken with the state psi. Sorry, psi, and this should be taken in the state psi.
Let's rewrite that.
So we take the commutator, we take the expectation value in our state, we take the norm, multiplied by 1/2, and this is the background, this is the commutator. So let's check this in the case of X and P. And we'll derive this using just math. This will come from just linear algebra. So let's check this in the case of X and P. What's the commutator? 1. So what's the expectation value of the state psi of IH bar times the operator 1 psi? It's IH bar. So what happens over here? What do we get for delta X into the state psi times delta P?
1/2 H bar over 2.
This must be greater than or equal to 1/2 times the absolute value of the expectation value of the commutator. The expectation value of the commutator is IH bar, and the norm of that is just H bar. This is the uncertainty relation. So given some uncertainty about the X, this tells us how much delta is. Now, how does this right-hand side depend on the wave function psi? Well, it turns out it doesn't. Right? It's explicitly independent of the impeding wave function we're interested in. For any wave function, whatsoever, the uncertainty in X times the uncertainty in P must be greater than or equal to 1/2 H bar. And this is a consequence of the commutation, and more importantly, the failure of X and P to commute. Because the ability to commute and get 0 is necessary for there to be common eigenstates. Now imagine, in this case, A and B are that A and B, that in fact do share a common eigenstate. So let's compute the expectation value, or the uncertainty of A in the state phi sub AB. Phi sub AB, phi sub AB, phi sub AB. And what is this equal to? Well, what's the commutator acting on the state phi sub AB? 0. So this is greater than or equal to 0. And in fact, you can just check by going through the proof of this that it's just equal to 0. So what's the uncertainty of A? Well, we know it's in a state with definite value A, 0. Uncertainty in B in the state, what's the uncertainty? 0. We know that it's in an uncertainty B. So 0 is indeed greater than or equal to 0. So it satisfies the uncertainty relation. Commuting is telling you about the possibility of the state having definite values of both operators simultaneously. And this is going to turn out to be enormously valuable when we talk about angular momentum, which is coming in a couple of weeks. Okay, see you guys on Thursday here for the midterm.
All right, so I'm just going to jump back here. Yeah, I went a little bit longer today than I thought, but I really wanted to get done all 10, well, not all 10, the first 10 lectures so that we can move to problem sets. So now I can bookend this. If we're talking about what are still some gaps in the understanding? Well, based on the clicker questions, I'm doing pretty good. There was a section here about orthonormal bases and this thing here, which I made a ton of, which I didn't quite understand. This one here, I got it wrong because I just didn't know what this Hamiltonian operator is, and he cleared that up after the question. So I'm not going to be too hard on myself there. This one too, I think, was a fairly silly mistake. And this one I also got wrong, but it was, to be explained after. So in terms of the self-testing material from the test, we're doing okay. I think it's just understanding the brute force method for the partial differential equation of the energy eigenstates, and then also the kind of raising lowering operator method that we did using the operator method. Those I'm not as strong on, but they're kind of complicated. As I said, I think what I'm probably going to do is just jump forward, do the problem sets, try to go through problem sets 1 to 5, see how those feel. I may need to do some extra learning for problem set 1 of all things, because problem set 1 I think depends a little bit more on previous classes, in particular 803 that I didn't do. So we'll try those out. I think I'm going to jump around. I've got basically tomorrow afternoon, Thursday, Friday to hopefully be done. First 5 problem sets. I might also write the midterm exam that he's mentioning in the class, although I may save that for later. I'm not sure whether I'm going to do that in this set before I move on. I'll just see how the problem sets feel. If problem sets felt pretty easy, I might save the midterm just because it'll be good refresher practice after I move on to doing different techniques. And we'll see if things are breezing through and I feel like I can get through the problem sets pretty quickly and we're done, let's say before the end of Friday, I might devote an hour or two to going through these 2 sort of shaky spots. On the same sense, I'm just going to kind of feel if the problem sets felt really hard, I might slow things down, stretch the lectures out a little bit more, because lacking understanding is going to impede understanding the rest of the class. If the problem sets felt pretty easy, then my difficulties with understanding all of these partial differential equations and all that kind of stuff is maybe not as important. So, I'm just going to take just a quick second to look through some of the comments. I know people were commenting on some of the things here. I know Eshes is commenting that it's kind of hard to follow the experiment. I'm not really expecting people to be learning at the same time as me in exactly the way I'm doing it. This is more to showcase how I'm learning it. If you want to actually learn these classes, best thing to do is kind of what I'm doing, but not watching my live stream. Like, set your own lecture, choose your own pace, solve your own problems. I'm hoping this is just going to be more illustrative than that you're actually learning along with me at exactly the same speed, because I'm speeding through things that I understand, and I'm slowing through things that I don't understand. The things that I don't understand, the things that I do understand are going to be different than you. So this is a big part of what I kind of recommend, is this sort of personalizing the process, adjusting based on the feedback of your environment. If you have less prerequisites or less familiarity than I do, this might be way harder than it is for me. And if it's way harder than it is for me, you might need to do a whole class first or something like that. Laura said, talk about working with the textbook. I don't know how much I'm going to be working with the textbook. I'm going to be honest with you. I do have this textbook here, but there's no readings corresponding to the ones in the class. So there might be a little bit of page flipping to see if I have correspondences with what's being done here. Again, if I can find a section that goes over the kind of brute force partial differential equation solution, this could be a good companion, because I felt like I don't know whether there's class notes for that lecture, and it was a little bit elaborate, so it was a little bit like went over my head. But you know what? I think this is good for now. I'm going to take a lunch break, do some work for a change, and then I'll be back at 2 p.m. To conclude this afternoon, where we're going to move on to the problem sets.